There exists a star so extreme, so close to the edge of physics, that it nearly tears itself apart every single moment of its existence. This isn't a metaphor or exaggeration, it is a literal description of VFTS 102, the fastest spinning massive star ever observed in the known universe. If you were to witness this star up close, you wouldn't see a calm, glowing orb like our sun. You'd see a cosmic storm, matter flung sideways at impossible speeds, a shape distorted by violence, and a glow that pulses with raw power. VFTS 102 is not just a star, it is an ongoing astrophysical event, a mystery written in the language of speed, mass, and energy. But before we continue, subscribe to the channel. To understand VFTS 102 is to glimpse a limit of nature itself. Stars aren't supposed to spin this fast. At around 600 kilometers per second, over 2 million kilometers per hour, VFTS 102's surface is whirling at a speed so close to the theoretical breaking point, it's as if nature dared itself to go just one step further. The critical speed for a star is the point at which the outward centrifugal force from its rotation overcomes the inward pull of gravity. Most stars never approach this line. VFTS 102 is practically dancing on it. Why is that significant? Because stars, especially massive ones, are generally expected to form and evolve within a fairly consistent range of behaviors. Their mass, composition, temperature, and rotation usually fall within predictable parameters. But VFTS 102 is a renegade, a star that challenges the very foundations of those parameters. And the more we learn about it, the more it seems like it shouldn't exist at all. This star offers us a chance to peer into a realm where the known laws of stellar evolution start to strain and warp. It's like watching a race car flying down a track where the engine should fail, the tires should burn, and the car should flip, but somehow it stays on course, daring physics to catch up. If our sun is a quiet country road, then VFTS 102 is a twisting track at full throttle, with no brakes. Even its appearance would be alien. Its surface, distorted by its tremendous spin, wouldn't be spherical but stretched, flattened at the poles and bulging at the equator. Its light would not be uniform but uneven, shaped by its extreme conditions. And inside, the chaos is even greater. This isn't just a fast star. It's a cosmic anomaly, a laboratory of extremes, and a ticking time bomb. And what's even more fascinating is the implication: something must have made it this way. Stars don't just start spinning at such speeds by chance. There's a story behind VFTS 102, one of cosmic violence, loss, rebirth, and motion. We'll dive into all of it. Its location, its physics, its past, and most chilling of all, its future. Because VFTS 102 is not just spinning. It's spiraling toward a spectacular end. One day, this star may collapse in on itself and unleash a gamma-ray burst, a beam of energy so powerful, it can sterilize entire solar systems. It could become one of the most destructive forces in the universe. So what is this star? What secrets does it hold? How did it come to spin so furiously? And what does it tell us about the forces that shape our cosmos? This is the story of VFTS 102, the star that defies limits. Far from Earth, in a corner of the southern sky barely visible to the naked eye, lies a sprawling, energetic region of star formation, a stellar nursery unlike almost any other in our local universe. This region, known as the 30 Nebula, pulses with the raw ingredients of cosmic creation. It's immense, it's chaotic, and it's beautiful in the way that only something both dangerous and alive can be. Astronomers have another name for it, the Tarantula Nebula. A fitting title, not just because of its web-like filaments of glowing gas, but because it's a place where stars are born fast, live fast, and often die violently. The Tarantula Nebula is located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 160,000 light-years away. Though it lies outside our own galaxy, the Tarantula Nebula is close enough, and massive enough, that it has captured the full attention of astronomers for decades. It's the most active star-forming region in the entire local group of galaxies, which includes the Milky Way, Andromeda, and dozens of other smaller galactic neighbors. In essence, it's a cosmic powerhouse, a laboratory where we can study how the most massive and energetic stars in the universe come to be. And nestled deep within this electrified cradle of stellar activity is VFTS 102. It's almost poetic. This star that lives on the edge, spinning at near-destructive speeds, was born in a place equally extreme. The Tarantula Nebula is not a calm nursery of softly glowing gas. It's a roaring forge where radiation pressure, magnetic turbulence, and violent shockwaves carve out new stars in rapid succession. VFTS 102 is a product of that chaos. The gas and dust that collapsed to form it likely did so under immense pressure and heat, conditions ripe for giving birth to massive stars, and to anomalies like this one. But the nebula didn't just give VFTS 102 a place to form. It also gave it context. The nebula is filled with other high-mass stars, including a supercluster known as R136, where some of the most massive stars ever discovered reside. It's a cosmic zoo of giants, each with mass dozens or even hundreds of times greater than the Sun. This neighborhood is not gentle. The winds from these stars collide. Supernovae rip open the clouds. Radiation strips away gas from neighboring systems. It's a survival of the fittest ecosystem for stars. And yet, even in this dramatic setting, VFTS 102 manages to stand out. Amid the roiling gas of 30 Doradus, where ultraviolet radiation pours like a storm and stellar winds crash like waves, this one star, this furious, rotating enigma, commands attention not by its mass alone, but by its motion. It's not the biggest. It's not the brightest. But it is the fastest. And that distinction makes it one of the most important. The Tarantula Nebula provides the backdrop for this story, not just as a birthplace, but as a stage for ongoing transformation. As we look deeper into VFTS 102, we'll see how its environment may have helped shape it, and how it may, in turn, impact the nebula around it. The light that pours off its surface carries information across space, across time, reaching us as a whisper from one of the most volatile stellar nurseries known to science. In the vast field of stellar observation, where billions of stars have been catalogued and classified, only a few ever make history. Among them, VFTS 102 holds a title that has yet to be challenged. It is not merely fast, it is, by current scientific consensus, the fastest spinning massive star ever discovered. That alone places it in a category so exclusive it stands virtually alone. At its equator, this star rotates at a blistering speed of approximately 600 kilometers per second. That's a number that forces you to pause. Not just because it's large, but because it bends our sense of what's physically possible. When astronomers first measured this rotation speed, they were stunned. This wasn't just a small bump above the average, it was a radical outlier. Something so extreme that it demanded a complete re-examination of everything thought to be true about stellar rotation. To put things into perspective, most massive stars spin at rates closer to 100 or 200 kilometers per second. Some reach 300 or 400 kilometers per second and are already considered fast rotators. But VFTS 102 exceeded even those outliers by a massive margin, nearing what's called the critical velocity, the point at which a star would lose its ability to hold itself together under its own gravity. The number, 600 kilometers per second, is more than a measurement. It's a statement. It says that this star is operating on a razor's edge, where centrifugal force is tugging at its outer layers with such aggression that one more push could cause material to be ejected into space. There's no known massive star with a confirmed spin rate higher than this. Not in the Milky Way. Not in the Large Magellanic Cloud. Not in any nearby galaxy ever studied with this level of precision. It's worth emphasizing just how precise these measurements are. VFTS 102 was studied using spectroscopy, specifically, by analyzing the Doppler broadening of its spectral lines. As parts of the star's surface move toward us and away from us at different speeds, the light shifts in wavelength, creating a broadened spectral signature. For VFTS 102, this broadening was extreme, evidence of a rotation rate never before seen in a star of its size and mass. The data was so clear, so undeniable, that the designation of fastest spinning massive star wasn't just speculation. It was confirmed, measured, and recorded. And being a record breaker matters. Because records are how we test the boundaries of science. When a star like VFTS 102 shatters the expected maximum for rotation, it means something fundamental about our models needs to change. How did it get that fast? Why hasn't it flown apart? What does that speed mean for its internal structure, its future evolution, and its ultimate fate? In the realm of high-mass stars, objects already known for their instability and short, explosive lives, VFTS 102 is a standout. It's like discovering a sprinter who not only runs faster than anyone else alive, but runs at a speed you thought the human body couldn't survive. Its existence forces us to reconsider what is possible in the life of a star. Let's take a moment to truly grasp what 600 kilometers per second actually means. Numbers like these can be thrown around so casually in astronomy that we often become numb to their enormity. But this number is anything but ordinary. It is staggering. It is extreme. And it describes a physical phenomenon that pushes the very limits of what the universe allows. 600 kilometers per second translates to over 2.1 million kilometers per hour. That's not just fast. That's incomprehensibly fast. If something were to move at that speed across the surface of Earth, it would complete a full orbit of the planet in just about 1 minute. A trip from New York to Tokyo? Less than a second. A journey to the Moon, a distance of roughly 384,000 kilometers? That would take just over 10 minutes at VFTS 102's equatorial speed. At that rate, you could travel from Earth to the Sun, a span of about 150 million kilometers, in under 3 days. For comparison, light itself, the fastest thing in the universe, takes around 8 minutes to make that same trip. VFTS 102, while nowhere near light speed, still moves at a pace that dwarfs anything in our human experience. But here's the crucial difference. VFTS 102 isn't moving through space at 600 kilometers per second. Its surface is rotating at that speed. That is, every point along its equator is being flung around in a massive circular motion at over 2 million kilometers per hour. This is a star, not a spaceship. It's not going anywhere in a straight line. Its outer layers are spinning around its axis so quickly that they're almost detaching from the body of the star itself. Imagine our Sun, a sphere of superheated plasma, rotating so fast that it starts to flatten, to bulge at the middle, and to shed its upper layers into orbit. That's what VFTS 102 is doing, or rather, on the verge of doing. It is barely holding together. This brings us to an important concept in astrophysics, the critical rotational velocity. This is the speed at which the centrifugal force at the star's equator equals the gravitational force pulling inward. If a star spins faster than this limit, its equatorial material is no longer gravitationally bound and will be thrown into space. For most stars, this limit is far above their actual rotational velocity. But for VFTS 102, it is almost precisely at this threshold. One nudge, one burst of internal pressure, one magnetic fluctuation, one ripple in its structure, and it could start losing mass explosively. And that's not just a theory. Stars like this are believed to create equatorial disks of ejected material. In fact, some evidence already points to subtle signs of material possibly being flung outward, forming faint rings of gas that glow in ultraviolet. To say the star is on the edge is not metaphorical, it is literal, physical, and immediate. The atoms at its equator are being hurled outward so quickly that gravity is having to work overtime just to keep them from flying off. Any faster, and those atoms would be gone. That raises an even more intriguing question. Why isn't it already disintegrating? How does it maintain such an extreme spin without collapsing or losing significant mass? The answer is that it's probably not sustainable. Stars like VFTS 102 don't live long, and they certainly don't live peacefully. The incredible spin is likely a phase, a result of a violent past, which we'll explore soon, and it may already be slowing, ever so slightly, through the loss of angular momentum via stellar winds. But for now, in the present moment, it's spinning at the fastest confirmed speed ever recorded for a massive star. And that speed makes it one of the most important laboratories in the sky for testing our understanding of astrophysical limits. To understand the physical impact of such speed on a massive star, we need to imagine not just the surface speed, but the forces at play inside. The centrifugal force at the equator is attempting to unbind the outer layers. Inside, nuclear fusion is raging, generating light and pressure. The intense rotation alters the internal flow of gas, redistributing heat, elements, and momentum. Convection cells, those vast, churning motions inside stars, become elongated and distorted. The rotation drives turbulence, changes the magnetic behavior of the star, and can even warp the pathways by which elements are formed and transported. This speed also directly affects the shape of the star. We'll explore that in more depth soon. But suffice it to say, VFTS 102 is not a perfect sphere. It can't be. A star rotating this fast must be significantly flattened at the poles and bloated at the equator. This distortion affects everything about its physical properties, from surface temperature to emitted light to the behavior of surrounding stellar winds. We're looking at an object that is being twisted by its own velocity into something fundamentally different from normal stars. And this velocity isn't just a freak anomaly. It has consequences for the star's long-term evolution. Rapidly rotating stars evolve differently from their slower counterparts. The way they burn fuel, the way they age, the way they die, all are altered by spin. High rotation rates can mix the inner layers more efficiently, dragging fresh hydrogen into the core and prolonging the fusion process. That can make the star live slightly longer, but it also changes its chemical composition and the way it loses mass. The fate of a fast rotator like VFTS 102 is not the same as that of an ordinary star of similar mass. When it finally runs out of nuclear fuel, its collapse could lead to something extraordinary, perhaps a long-duration gamma-ray burst, the most violent kind of stellar death in the universe. And yet, despite its extreme speed, VFTS 102 remains mostly intact, for now. This delicate balance it maintains, teetering at the edge of self-destruction, is what makes it so compelling. It is a cosmic dare, a massive, glowing threat that hurls its outer layers at the very speed limit of gravity's ability to hold them down. There is no other known object in its class with this degree of rotational intensity. Every new measurement, every spectral line, every image we collect from its light is a clue to a larger mystery: how nature created such a thing, and what will ultimately become of it. Because when we say that 600 kilometers per second is fast, we don't just mean fast in human terms. We mean fast in the context of a universe that includes neutron stars, black holes, and galactic collisions. We mean that this star is pushing against the fabric of stellar stability itself. And in doing so, it gives us a chance to witness physics at its breaking point, a rare and irreplaceable glimpse into the upper limits of cosmic motion. VFTS 102 doesn't just spin fast, it spins so furiously that it exists in a permanent state of tension, where the very structure of the star is held together by a fragile balance between two titanic forces: gravity pulling inward, and centrifugal force trying to fling it apart. At its equator, the star is rotating at a speed perilously close to what astrophysicists call the critical velocity, a physical threshold that defines the maximum spin a star can sustain before it starts to lose control of its own outer layers. This critical rotation speed is not arbitrary. It is calculated based on the mass of the star, its radius, and the strength of gravity at its surface. It is the point at which the centrifugal force due to rotation becomes equal to the star's surface gravity. In simpler terms, once a star hits its critical speed, the force trying to pull the star's outer layers outward becomes just as strong as the force trying to hold them in. If it crosses that threshold, those outer layers are no longer bound to the star, they are ejected into space. For VFTS 102, this threshold is not some distant theoretical limit, it's a razor-thin line the star is already brushing up against. Estimates suggest that the star is spinning at over 90% of its critical velocity. That's not just fast. That's cataclysmic. It's as though the star is permanently walking on a tightrope. Any slight disturbance, internal pressure shifts, turbulence, instability in the fusion core, could cause it to shed mass, disrupt its shape, or even accelerate its path to death. We have examples of stars that have crossed this line. These are known as B stars, and they frequently show signs of having formed gaseous disks of expelled material around their equators. This is a direct result of their spin exceeding the gravitational containment limit. In these cases, we actually see the star's own substance, ionized gas, flung into space and then lit up by the star's radiation, forming beautiful glowing rings. VFTS 102, based on current observations, hasn't quite crossed that boundary. But it is right there, skirting the edge, possibly already beginning to experience subtle mass loss in ways we can't yet fully detect. The fact that it hasn't visibly started to fling off its atmosphere makes it an even more fascinating object. It tells us something about the unique interplay of conditions holding this star together. Its internal gravity is just barely doing its job, gripping the layers of plasma along its equator with the tiniest of margins. That's an incredibly unstable configuration. Stars don't maintain that balance for long. Something will change, eventually. And when it does, the consequences could be dramatic. What makes this even more fascinating is how non-uniform the stress across the star is. Because of the centrifugal force, the equator experiences vastly more stress than the poles. At the equator, particles are being thrown sideways at incredible speeds. At the poles, however, where the radius of rotation is much smaller, the effect is far less severe. This differential rotation stress is what contributes to the flattening of the star, creating a distorted shape, more oblate than spherical. It also sets up the potential for equatorial mass loss, where the weakest parts of the gravitational grip are first to give way. Imagine the surface of the star not as a smooth glowing sphere, but as a turbulent, unstable sea of plasma, rippling and flexing under immense forces. The equatorial regions are stretched outward, thinned, and constantly strained by motion. Any localized explosion or disturbance, say, a flare or a burst of magnetic activity, could be the trigger that tips the balance. A minor fluctuation in temperature or density could mean the difference between stability and a violent shedding of mass. And once that shedding begins, it may not stop. A runaway feedback loop can occur, mass is lost, which reduces the gravitational binding, which makes it easier to lose more mass, which further reduces the containment strength. Eventually, the star could form a circumstellar disk, an envelope of expelled material orbiting the star's equator like a luminous ring. This disk can then be reabsorbed, blown away by radiation pressure, or become the birthplace of complex plasma structures. But there's another, even more profound implication of spinning so close to the critical limit: how it changes the star's internal fusion dynamics. In a normal star, the fusion process in the core pushes outward while gravity pulls inward, maintaining a stable equilibrium. But in a near-critical rotator like VFTS 102, that equilibrium is complicated by spin. The rotation causes differential mixing of stellar layers, which can drag hydrogen from the outer layers into the core and spread heavier elements outward. This dramatically alters the star's evolution. It may burn its fuel in strange, unpredictable ways. It may skip expected evolutionary phases. It may die younger, or it may appear younger than it is, a phenomenon known as rejuvenation. This spin-induced instability doesn't just affect the star. It also affects the space around it. The intense motion stirs up stellar winds, generating high-speed outflows of charged particles. These winds can smash into the interstellar medium, producing bow shocks and shock fronts. They can ionize nearby gas, adding to the glow of the surrounding nebula. In essence, VFTS 102 isn't just sitting quietly in the Tarantula Nebula, it's actively sculpting it. The star's behavior, its proximity to self-destruction, and its interaction with its environment turn it into more than just an astronomical curiosity. It becomes a case study in extremity, a place where astrophysics meets its stress test. When we model stars, we assume certain balances of forces. But here is a natural object where those forces are in open conflict. Here, we see what happens when the balance is fray, when the structure becomes dynamic, and when a star spins so fast that it becomes a hazard to itself. And yet, VFTS 102 remains, brilliant, wild, and spinning just shy of death. It gives scientists an unprecedented opportunity to witness a star not merely existing, but actively testing the edge of stellar stability. It's a cosmic tightrope walker with no safety net, and with every second that passes, it continues its high-wire act above the abyss of self-destruction. VFTS 102, in its relentless spin, doesn't simply glow like a perfect sphere of light suspended in the darkness of space. It is distorted, stretched, and sculpted by the forces acting upon it. At speeds nearing 600 kilometers per second, the star's rotation alters more than just its surface velocity or outer atmosphere. It fundamentally reshapes the star itself. The VFTS 102 is not round. It is oblate, a shape better described as an ellipsoid or flattened spheroid, bulging at the equator and compressed at the poles. This phenomenon, called stellar oblateness, is a natural consequence of rapid rotation. In any spinning body, whether it's a planet, a star, or even a spinning coin, centrifugal force acts outward from the center of rotation. For stars, which are enormous balls of plasma and gas with no solid surface to speak of, that force can dramatically alter their geometry. The faster a star spins, the more pronounced the distortion becomes. For VFTS 102, already operating close to its critical velocity, the deformation is extreme. At its poles, gravity wins the fight, holding the star tightly inward. But at the equator, where centrifugal force pushes the strongest, gravity is barely able to restrain the outward motion. The result is a star that may appear nearly 20% wider at the equator than it is tall from pole to pole. That's not a cosmetic difference, it is a structural transformation that redefines how the star behaves, how it radiates energy, and even how we interpret its brightness. This distortion doesn't just affect the shape, it affects everything about the star's physical environment. Because the equator is farther from the star's center than the poles, the surface gravity is weaker there. Weaker gravity leads to cooler temperatures. Cooler temperatures, in turn, result in dimmer radiation. Meanwhile, at the poles, where gravity is stronger and centrifugal force is minimal, the surface is hotter and brighter. This temperature gradient across the star's surface leads to a phenomenon known as gravity darkening, a topic we'll explore more in the next segment. But even beyond gravity darkening, the oblateness of VFTS 102 creates deep implications for how the star functions internally. Inside, fusion doesn't operate in a calm, spherical core. The intense spin can cause mixing of material across layers that normally remain isolated in slower spinning stars. This mixing brings hydrogen fuel from the outer envelope into the core, while dredging up heavier elements from the interior toward the surface. This kind of internal convective blending reshapes the star's life cycle, potentially prolonging its core fusion phase but also creating unpredictable variations in brightness and temperature. This shape, this deformation, may not be visible in the way we imagine seeing planets or moons through telescopes. We don't have images of VFTS 102 like we do of the Moon or Mars. But its oblateness is revealed through spectroscopic signatures, the way its light spreads out across different wavelengths. As the star spins, parts of its surface move toward us while others move away. The resulting Doppler broadening tells us how fast those surface regions are traveling, and more importantly, how those speeds vary across the surface. From this, astronomers can model not just the spin, but the resulting distortion in its structure. And those models tell a remarkable story. VFTS 102 is not just spinning at a record pace, it is structurally warped by that spin. In many ways, its oblateness is the most visually alien aspect of the star. We are used to thinking of stars as spheres, perfect and serene, glowing uniformly in all directions. But VFTS 102 challenges that idea. If we could see it up close, it would not resemble a sun-like orb. It would be wider than it is tall, glowing unevenly, with its shape dictated not by symmetry, but by motion. This distortion also affects the surrounding space. The equator, being the point of maximum outward thrust, is the most likely region for material to be ejected should the star reach or exceed its critical rotation speed. The oblateness essentially defines the regions of vulnerability on the star's surface. If VFTS 102 does begin to lose mass, or if it already has begun, it would likely be from this widened, lower gravity equatorial zone. Even the magnetic field geometry may be affected. Rapid rotators tend to generate complex, often weaker surface magnetic fields. Because of the oblateness, the magnetic field lines can become twisted, contorted, and uneven. This could be one reason why VFTS 102 does not show signs of the powerful magnetism that might be expected from a star spinning so fast, an anomaly we'll also explore later. It's worth reflecting on what this shape truly means in a cosmic context. When you observe a star like this, you are witnessing an object sculpted by motion, not by stasis. Every particle of matter on its surface is being flung sideways at unimaginable speeds, and gravity is just barely holding the structure together in a constantly shifting equilibrium. It is not a quiet object, it is a violent one, caught in a state of high-speed tension. It is, in every sense, stretched to its limits. And this shape is not just a static condition. It changes. As the star evolves, losing angular momentum, shedding mass, altering its internal pressure gradients, its oblateness may become more or less pronounced. If VFTS 102 slows down, the equator could contract. If it speeds up, even slightly, the bulge may increase, bringing it even closer to the threshold of disintegration. In a way, the shape of VFTS 102 is a map of its struggle. A silent record of the war between gravity and motion, each trying to dominate the other. And as long as it continues to spin at this unimaginable pace, it will remain caught in that struggle, reshaped by its own refusal to slow down. The distortion of VFTS 102 into an oblate shape does more than reshape its appearance. It also sculpts the very way it radiates light into the cosmos. One of the most visually and scientifically striking consequences of such extreme rotation is a phenomenon called gravity darkening. This is not a poetic description, it is a measurable, observable difference in brightness and temperature across the star's surface, rooted in deep physical principles. And in VFTS 102, spinning near its critical velocity, this effect is pushed to its absolute extremes. To understand gravity darkening, we need to return to the core of what's happening. The star's spin is flattening it at the poles and bulging it at the equator. That distortion means that surface gravity, how strongly the outer layers of the star are held in place by gravity, varies depending on where you are on the star. At the poles, gravity is stronger because the material is closer to the center of mass and the centrifugal force is minimal. At the equator, the centrifugal force is so powerful that it nearly cancels out gravity, and the surface is farther from the star's core, which weakens the gravitational grip. This variation in surface gravity leads to a variation in temperature. Stronger gravity at the poles compresses the plasma more tightly, increasing pressure and temperature. Weaker gravity at the equator allows the plasma to expand and cool. The result is a star with hot, bright poles and a cooler, dimmer equator. If you could look at VFTS 102 with your own eyes, ignoring the obvious danger of being incinerated, you would not see an evenly glowing orb. You would see a glowing, misshapen star with an intense, searing brilliance at its top and bottom, and a faint, reddish belt circling its middle. In stars like VFTS 102, this difference can be extreme. The poles might reach temperatures of over 40,000 Kelvin, while the equator could be tens of thousands of degrees cooler. That's a massive contrast, more than enough to shift the color, radiation profile, and emitted spectrum of the star depending on where you're looking. This has deep implications not just for how the star looks, but for how we interpret it. If astronomers view the star from different angles, say, aligned with its equator versus aligned with its pole, they will measure different brightness levels, different color temperatures, and even different apparent sizes. In fact, orientation matters a great deal when observing a gravity-darkened star. If we see VFTS 102 more from the side, along its equator, we're primarily seeing the cooler, dimmer region. If we happen to be looking more pole-on, we're getting a face full of its brightest, hottest surface areas. That means a single star can look like a different type of star depending on your viewing angle, an observational challenge that complicates classification and analysis. In extreme rotators like VFTS 102, this variation isn't just noise, it's a fundamental property that has to be accounted for in every model. This temperature and brightness differential also changes how energy escapes from the star. At the poles, where gravity is strong and the plasma is dense, radiation escapes efficiently. At the equator, the lower pressure and expanded layers make it harder for photons to escape. That means the poles not only shine brighter, they also shed more energy, leading to a complex interplay between rotation, structure, and radiative output. Gravity darkening has been observed in other stars too, but only a few show it as strongly as VFTS 102 is expected to. Observational techniques like interferometry, which allows astronomers to measure the actual shape of nearby stars, have confirmed this effect in stars such as Altair and Vega. But those are relatively modest rotators compared to VFTS 102. In this star, the phenomenon is amplified to a level that pushes against the edges of our understanding. The equator isn't just dimmer, it's a different kind of stellar surface, governed by weaker gravity, cooler temperatures, and different radiation dynamics. Even the star's winds and magnetic behavior are affected by gravity darkening. The poles, being hotter and under greater pressure, generate stronger outflows of charged particles. The equator, meanwhile, may exhibit denser, slower-moving winds, or in some cases, act as a reservoir where expelled matter lingers. This creates a complex atmospheric structure, where the poles are driving high-speed stellar wind into the surrounding nebula, and the equator may be forming denser, disk-like regions of accumulated material. From an evolutionary perspective, gravity darkening also plays a subtle but important role. The uneven temperature distribution alters how the star fuses elements in its core and how it transports energy from the interior to the surface. It even impacts how mass is lost over time, a key factor in how long a massive star lives and what kind of explosion it will produce when it dies. For example, stars with pronounced gravity darkening may experience asymmetric mass loss, meaning they lose more material from one region than another. This could lead to asymmetric supernova explosions or highly focused jets of material, perhaps even contributing to the formation of long-duration gamma-ray bursts. In VFTS 102, gravity darkening isn't just an aesthetic feature, it's a signature of the physics tearing at the heart of the star. It's a thermal fingerprint left by a star pushed to the edge of cohesion. The brighter poles are like cosmic beacons, radiating intense ultraviolet light that bathes the nearby gas clouds of the Tarantula Nebula. The dimmer equator, in contrast, seems almost to retreat from the violence, offering a thin veneer of stability amid the storm. Yet together, they tell the story of imbalance, of a star that, due to its speed, cannot be at peace with itself. And this imbalance may be increasing over time. As the star evolves, burning through its nuclear fuel, shifting its core structure, perhaps even interacting with remnants of past collisions or companions, the gravity darkening could become even more extreme. Or it may fade, if the star slows its spin through mass loss or magnetic braking. For now, though, we are seeing VFTS 102 at a rare moment in its life, a star spinning so fast, it lights unevenly, cools unequally, and lives out its violent youth painted in gradients of heat and light. This uneven illumination, this visual warping of brightness across a star's body, reminds us that nature rarely favors symmetry. Especially not in a place like the Tarantula Nebula, and not in a star like this. In VFTS 102, motion has sculpted a canvas of light where nothing is uniform, and everything speaks to the struggle between balance and chaos. Though VFTS 102 dazzles us with its ferocious spin and distorted structure, another essential trait adds to its staggering cosmic presence: it is massive. Not just heavy in the way all stars are, but categorically, almost recklessly massive. Based on spectral analysis and modeling of its luminosity, surface temperature, and gravity, astronomers estimate that VFTS 102 possesses around 25 times the mass of our Sun, and possibly even more depending on how the star's inclination angle is affecting our observations. To put that into perspective, this one star contains the equivalent mass of 25 full-fledged solar systems. If you tried to place it where our Sun sits, its gravitational influence would completely rewrite the architecture of the solar system. The planets, moons, and debris fields would be thrown into chaos, or perhaps consumed altogether. Mass in stars isn't just a number, it is destiny. The mass of a star determines how hot it gets, how quickly it burns through its nuclear fuel, how violently it ends, and even whether it leaves behind a white dwarf, neutron star, or collapses into a black hole. And the upper end of the stellar mass spectrum, where VFTS 102 comfortably resides, is a realm governed by intensity and brevity. These stars are not long-lived. They're not meant to be. They live hard, burn hot, and die young in violent, universe-shaking deaths. VFTS 102, despite being a cosmic titan, is still young, likely just a few million years old. In human terms, that might seem ancient, but in cosmic time, it barely registers. The Sun, by comparison, is about 4.6 billion years old and is expected to live another 5 billion years. VFTS 102, with its massive size and extreme rotation, probably won't even reach the age of 10 million years before it exhausts its fuel and collapses in some form of cataclysmic event. It's still in what we might call its stellar adolescence, a rapidly evolving phase marked by intense nuclear burning, powerful radiation, and dynamic internal changes. What's important to understand is that being both massive and young gives VFTS 102 an unusual kind of volatility. It's like a fusion-powered engine that's only just revving up, but already near its red line. Its core is converting hydrogen into helium via the CNO cycle, carbon-nitrogen-oxygen, a highly temperature-sensitive form of fusion that dominates in high-mass stars. This reaction is far more efficient, and far more violent, than the proton-proton chain reaction that powers smaller stars like our Sun. The result is an incredible output of energy, flung outward as radiation, stellar wind, and particles that shape the space around it. Because it is young, VFTS 102 has not yet entered the later stages of stellar evolution, such as the red supergiant phase, or the core helium-burning phase, that older massive stars pass through. It is still predominantly a main sequence star, albeit a very extreme one. This stage is where a star spends the majority of its life, stably fusing hydrogen into helium in its core. But in the case of VFTS 102, the term stable applies loosely. The core might be in balance for now, but the star as a whole is anything but calm. Its youth also means that it hasn't yet undergone significant mass loss, at least, not on the scale that will come later in its life. Massive stars like this tend to lose large fractions of their mass through intense stellar winds as they age, especially in the post-main sequence phases. But VFTS 102, still relatively early in its life cycle, retains most of its original mass, making it a pristine laboratory for understanding how massive, fast-spinning stars behave before they begin to unravel. Interestingly, its young age makes its extreme spin even more perplexing. Most stars tend to slow down as they age, losing angular momentum through stellar winds and magnetic braking. Yet VFTS 102 is spinning faster than any other known massive star, implying that something unusual must have happened during or after its formation. That's a puzzle we'll explore later in its possible past with a companion star, but for now, what matters is this: it's spinning at record-breaking speed right out of the gate. And that youth also opens a window into the early behaviors of massive stars more generally. Astronomers don't get to observe many stars like this at such a stage in their evolution, especially with such extreme traits. The combination of mass, speed, and age means VFTS 102 is like a time capsule, offering a glimpse of what the early life of stars in violent environments, like the Tarantula Nebula, might truly look like. It may also help us understand how some of the earliest stars in the universe, population 3 stars, which no longer exist, might have behaved. Those early stars were also massive, also fast, and also short-lived. Furthermore, the youth of VFTS 102 makes its current state all the more dangerous. Because the star is still relatively early in its life, it has plenty of nuclear fuel left, and with that, the potential to grow even more unstable. Over time, internal instabilities may develop, like convective bubbles, core contractions, or rotational mixing, that could push it past critical thresholds. Its youth is not a reassurance, it's a warning. The most violent stages of its life are likely still ahead. This combination of being young and massive is also one of the reasons astronomers are so focused on monitoring VFTS 102. It hasn't yet shown signs of collapse or runaway mass loss. But when it does, it might give us rare real-time data on what a massive, near-critical velocity star looks like as it begins to spiral toward death. It might not even need to evolve much further before becoming unstable. One subtle change, loss of mass through radiation, increased internal pressure, or a small burst of angular momentum from some hidden instability, could trigger a dramatic transformation. A disk might form. Bright jets might emerge. It could even become a Wolf-Rayet star, a class of highly evolved, stripped-down, massive stars that are shedding their outer layers before dying as supernovae. And that journey, from main sequence to collapse, will happen swiftly. We're witnessing VFTS 102 in a brief window of time, an incandescent heartbeat in the grand age of the cosmos. In a few million years it will be gone, transformed into something else entirely. A neutron star. A black hole. A gamma-ray burst. We can only speculate. But we know it won't remain as it is for long. In short, VFTS 102 isn't just fast, it's young and furious. A cosmic adolescent, full of energy, spinning wildly, still intact but already testing the limits of its own structure. And like all youth in the universe, it will not last forever. Despite all that we know about VFTS 102, its incredible speed, its massive size, its distorted shape and blistering surface, there's still a veil of confusion that clings to it, a persistent and puzzling mystery that refuses to be solved with simple models or conventional astrophysics. VFTS 102 is a star that shouldn't exist in its current state, at least not according to everything we thought we understood about how stars form, evolve, and die. It is, in the most literal sense, a star shrouded in mystery. The heart of that mystery lies in a simple but profound question: how did it come to spin so fast? Because stars do not typically form with this level of rotation. Even massive stars, which can be turbulent and energetic in their early lives, tend to exhibit more modest spin rates once their matter has coalesced from the collapsing cloud of gas and dust that birthed them. In fact, the formation process of stars naturally works to shed excess angular momentum, through magnetic braking, mass loss, and interaction with surrounding material. It's as if the universe wants stars to slow down a little before they ignite. Yet VFTS 102 defies that trend entirely. It rotates at over 600 kilometers per second, dangerously close to the edge of self-destruction. That's not just a deviation, it's an anomaly. It forces astronomers to ask whether something extraordinary happened in its past, something that catapulted it into this rarefied category of near-critical rotators. And that's where the mystery deepens. One hypothesis suggests that VFTS 102 may have been born spinning fast, possibly due to unusual initial conditions in its local stellar nursery. But this idea has significant issues. For one, the physics of star formation makes it difficult for a protostar to retain such high angular momentum without fragmenting or shedding material before reaching full maturity. And even if it somehow did, the star would likely have slowed down as it interacted with its surroundings, especially in a turbulent region like the Tarantula Nebula, where radiation pressure, nearby stellar winds, and magnetic fields are constantly jostling and breaking young stars. Another possibility is that VFTS 102 was spun up after its formation, perhaps by interactions with a companion. This is where things start to get more plausible and more intriguing. There's mounting evidence that VFTS 102 may have once been part of a binary star system, locked in a tight orbital dance with a similarly massive companion. In such systems, a range of complex interactions can occur, especially if one of the stars evolves faster than the other. One particularly violent event stands out, a supernova. But before we get to that possibility, let's reflect on why astronomers are so interested in this star in the first place. They've studied hundreds, thousands, of massive stars across multiple galaxies. They have sophisticated models that predict how fast stars of various masses should spin at different stages of their lives. And almost none of those models, under standard conditions, produce a result like VFTS 102. It's not just an outlier, it's a challenge to the theoretical framework itself. Spectroscopic measurements have been painstakingly analyzed to confirm that its rotation rate is not a fluke or a miscalculation. Its light is stretched and shifted in ways that unmistakably indicate rapid surface motion. Its spectral lines are broadened far beyond typical levels, and those distortions match exactly what you'd expect from a star spinning on the verge of structural failure. And that leads to a chilling realization: we don't fully know how nature created this object. Something unusual, perhaps violent, perhaps rare, must have shaped its present form. The mystery grows deeper when considering its environment. VFTS 102 is not located in a quiet, isolated patch of sky. It lives in the 30° region of the Large Magellanic Cloud, a chaotic stellar nursery where massive stars are born in clusters, live fast, and die young. It's a region with supernova remnants, strong radiation fields, and powerful shock waves rippling through space. Theoretically, such an environment could provide opportunities for unusual stellar interactions. Close flybys, mergers, mass transfer, or dynamical ejections could all play a role. But even among the stars in this wild neighborhood, VFTS 102 stands out. No other nearby star exhibits its same rotational behavior. This leaves astronomers in a tantalizing position. On the one hand, VFTS 102 is an observational gift, an opportunity to see what happens when a star is pushed to its rotational limits. On the other, it's an unresolved equation. Its spin doesn't match its profile. Its age doesn't match its instability. Its location doesn't fully explain its isolation. There is a missing piece, and finding it may teach us something new not just about stars, but about the laws of astrophysics themselves. There is also the unsettling idea that perhaps there are many stars like VFTS 102 out there, but we've missed them. If such stars are short-lived, faint at certain angles due to gravity darkening, or obscured by dust, they might not show up in surveys. VFTS 102 might be the tip of an iceberg, a clue that the universe occasionally creates stellar objects we've never fully accounted for. That idea is both exciting and daunting. It would mean revising our models for massive star evolution, rotational dynamics, and end-of-life scenarios. But what's most captivating about this mystery is how it draws together so many threads: rotation, mass, age, shape, temperature, and environment. Each factor plays a role, but none explain the whole. VFTS 102 remains a cosmic enigma, a star whose past is hidden behind veils of plasma, velocity, and time. And until we can fully unravel the forces that shaped it, the mystery remains alive. As astronomers probe deeper into the puzzle of VFTS 102's incredible rotation, one hypothesis began to rise above the rest, not just because it seemed plausible, but because it echoed a pattern observed in other stars that spin abnormally fast. It is the theory that VFTS 102 was once part of a binary star system, a tightly bound cosmic pair, where two stars orbited a common center of mass. This idea, supported by both physical models and indirect observational clues, might finally explain the star's otherwise inexplicable characteristics. But if true, it also means that VFTS 102's history was marked by tragedy, violence, and transformation. Binary stars are far more common than many people realize. In fact, more than half of all massive stars are thought to form in binary or multiple systems. These pairs don't just orbit one another in peace. They evolve together, and in some cases, dramatically reshape each other's fates. In such partnerships, particularly those involving massive stars, one star may evolve faster, swell up, and begin to transfer matter to its companion. And if this process occurs under the right conditions, it can cause one star to spin up, absorbing not only mass but angular momentum, which makes it rotate faster and faster. This is exactly what researchers believe may have happened with VFTS 102. Sometime in the past, long before we began observing it, VFTS 102 may have been the secondary star in a binary system. Its companion, slightly more massive, would have evolved more quickly, reaching the end of its hydrogen-burning phase while VFTS 102 was still in its youth. As the companion swelled into a giant phase, its outer layers would have spilled over, creating a stream of hot plasma spiraling into VFTS 102. This stream would have carried more than just material. It would have brought rotational momentum, causing VFTS 102 to spin up dramatically. We've observed similar behavior in so-called blue straggler stars and stellar clusters, stars that seem younger and faster than their neighbors because they've undergone mass transfer events. VFTS 102, however, may represent an even more extreme case. The companion star likely didn't just swell up. It may have reached the end of its life in a cataclysmic explosion. If it was massive enough, and if the binary orbit was close enough, then after transferring its outer layers to VFTS 102, it could have undergone a supernova, ending its life as a neutron star or pulsar and sending its former partner careening through space. This scenario neatly explains several of the otherwise inexplicable traits of VFTS 102. First, its extreme spin. Accretion of angular momentum from a companion star is one of the few mechanisms powerful enough to spin a massive star up to near critical velocity. Second, its status as a runaway star, which we'll explore in detail later, also makes sense. The gravitational shock of a supernova detonation can fling a surviving companion out of its original orbit, propelling it through space at high speed. And third, the possible presence of a nearby neutron star or pulsar, the ghost of its lost companion, lends further credence to the idea that VFTS 102 is not just an unusual star, but a survivor of a binary system gone violent. There are also chemical clues that point to this past. Stars that undergo mass transfer often show anomalous surface abundances, chemical fingerprints left behind by the fusion products of the former companion. Elements like nitrogen and helium may appear in greater quantities, mixed into the outer layers in ways that single-star evolution can't easily explain. If VFTS 102 shows such signatures, it would be a smoking gun for a history of binary interaction. Though data is still being collected, early spectroscopy hints at unusual chemical profiles that match this theory. In this light, VFTS 102 is not simply a fast-spinning anomaly. It is a relic of a cosmic partnership, one that ended in spectacular fashion. It was shaped by the death of another star, transformed by that star's end-stage shedding of mass, and launched into the universe with momentum it never would have gained on its own. It is, in essence, a rejuvenated star, reborn not through peaceful evolution, but through violent inheritance. There's something haunting about this idea. That the very thing that makes VFTS 102 so extreme, its incredible rotation, may be the result of a sacrificial act, an exchange of material from a dying star to a still living one. That its brilliance, its instability, and possibly even its future death as a gamma ray burst, all stem from a chapter of its life we can only piece together through indirect evidence. If VFTS 102 was part of a binary system, then its current loneliness is deceptive. Its path through space, its shape, its brightness, they all carry echoes of a missing partner. And while we may never witness that supernova or see the moment when mass transferred from one star to another, the clues left behind in the rotation, motion, and composition of VFTS 102 tell a powerful story. It's a story of transformation, of becoming something entirely new in the aftermath of catastrophe. It's a story written in plasma, velocity, and the slow unfolding of cosmic time. If VFTS 102 did indeed once belong to a close binary system, then the moment that likely defined its destiny, the moment that carved its name into astronomical records forever, was when its companion died in a supernova. This wasn't just a distant fireworks show in the vacuum of space. It was a violent and transformative event, one that shaped everything VFTS 102 would become. That explosion may have taken a system bound by gravity and torn it apart, flinging VFTS 102 into the cosmos with blistering momentum, while simultaneously supercharging its rotation. Supernovae are among the most cataclysmic events in the universe. When a massive star exhausts the nuclear fuel in its core, it can no longer support itself against gravity. The core collapses in a fraction of a second, and a massive outward shockwave blasts away the star's outer layers in an eruption so powerful it can outshine an entire galaxy for weeks. In a binary system, such an event is more than just an isolated death. It becomes a moment of dramatic cosmic interaction, altering the orbit, mass, and even spin of the surviving star. In the case of VFTS 102, the proposed supernova wouldn't have been a random celestial coincidence. It would have occurred in the intimate confines of a tight stellar binary, where the two stars orbited each other closely, perhaps with periods of just days or even hours. In such close proximity, as the now-dead companion swelled into a red or blue supergiant, it would have begun transferring mass to VFTS 102. This process, known as Roche lobe overflow, occurs when the outer atmosphere of one star exceeds its gravitational boundary and begins to spill onto its partner. That overflowing mass didn't arrive gently. It spiraled in, forming an accretion disk around VFTS 102, feeding material into its outer layers and injecting massive amounts of angular momentum. Imagine trying to drink from a fire hose of plasma moving at incredible speeds, except instead of damage, this star got faster, brighter, and hotter. The more mass it absorbed, the faster it spun. And in the final act of this cosmic duet, the companion underwent gravitational collapse and detonated in a supernova explosion. This is where things get even more intriguing. A supernova doesn't just end a star's life, it violently reshapes the surrounding space. The ejected mass can weigh several solar masses and blasts outward at thousands of kilometers per second. The force of this explosion can disrupt the gravitational bond between the stars. If the system loses more than half its total mass suddenly, as a supernova typically causes, the gravitational connection can break. The surviving star, VFTS 102 in this case, would be flung out of the system like a slingshot, its orbit shattered, and its path redirected forever. It becomes what astronomers call a runaway star. But it's not just the ejection that's significant. The angular momentum transfer from the accreted material before the explosion would have ramped up VFTS 102's spin to unprecedented levels. It may have been rotating fast already due to its own formation conditions, but the additional influx of mass and energy from the dying companion would have supercharged it. This is the most likely explanation for why VFTS 102 spins at near critical velocity, the maximum speed a star can rotate before it starts shedding its outer layers. It's a cosmic irony that the death of one star, an event meant to be final and devastating, could give such intense life to another. But that's the universe's way. The companion's destruction was, quite literally, VFTS 102's rebirth. The plasma that once composed its partner now races through its outer layers. The angular momentum of the original binary orbit is now encoded in its spin. And the explosion itself may have left behind a compact remnant, a neutron star or pulsar, possibly still visible near the Tarantula Nebula, a silent witness to the transformation it helped ignite. This idea is not just speculative. Astronomers have identified other stars believed to have been spun up by the same mechanism. In those systems, we often see a fast-rotating O or B-type star paired with a neutron star or pulsar, a telltale sign of a past supernova. VFTS 102 fits that template almost perfectly, with the added distinction of being the fastest rotator of them all. If this scenario is accurate, it would place VFTS 102 in a rare and violent lineage, one where stars are not just born and die, but transfer identity to one another in their final moments. Moreover, the consequences of this supernova connection may still be unfolding. The energy absorbed from the companion, the turbulence introduced by the accreted mass, and the rotational stress now pressing outward from VFTS 102's core all contribute to an uncertain future. It's as if the star is still processing what happened to it, still echoing with the aftermath of an explosion it barely survived. Its internal structure, altered by the mixing of new and old material, could be unstable. Its spin could still be edging closer to that critical threshold. And the legacy of the supernova might still be reshaping its final act, pushing it toward a gamma-ray burst, the most powerful type of stellar death known. In this light, the supernova isn't just an origin story. It's a triggering event, one that set VFTS 102 on a trajectory that no ordinary star could follow. The violent gift of another star's end gave rise to a uniquely extreme object, blazing, spinning, and unstable, with a history that continues to radiate through every photon it emits. VFTS 102 is a survivor. But not in the quiet, triumphant sense. It is a star that survived by absorbing the destruction of another. And now, it carries the legacy of that catastrophe, burning hotter, spinning faster, and racing toward an end that may be even more dramatic than the one that gave it new life. VFTS 102 doesn't just spin at a record-breaking pace. It also moves through space in a way that raises eyebrows across the astronomical community. It's not drifting gently in the stellar nursery where it formed. It's not lazily orbiting a galactic center or meandering within a cluster. No, VFTS 102 is bolting through space, carrying with it the scars and the secrets of a violent past. Its trajectory and velocity are not typical of stars born in calm environments. Instead, they point to something explosive, literally. This makes VFTS 102 what scientists call a runaway star. Runaway stars are celestial refugees, objects that have been flung from their birthplace at high speed. They don't simply wander off. They are ejected, usually with incredible force, often by supernovae or gravitational interactions. In the case of VFTS 102, the prime suspect is the former, the supernova explosion of its binary companion. That blast not only unbound the system, severing the gravitational link between the two stars, it also kicked VFTS 102, hurling it into interstellar space with momentum that even now defines its journey. Measurements of VFTS 102's radial velocity, how fast it's moving toward or away from us, have shown that it is traveling at a speed inconsistent with stars that simply formed in their present location. It's moving significantly faster than its neighbors in the Tarantula Nebula. When astronomers calculated its motion and compared it to other massive stars in the region, they found a peculiar divergence. VFTS 102 wasn't simply orbiting like the others. It was escaping, as if fleeing the scene of a cosmic crime. This movement is critical evidence supporting the supernova scenario we explored earlier. When a binary companion explodes, it releases an enormous amount of mass in an instant. If the system loses more than 50% of its total mass, the gravitational bond between the stars can no longer hold them together. The system disrupts, and the surviving star continues on in a straight line, propelled at its orbital velocity at the moment of detachment. But in some cases, especially if the supernova explosion is asymmetrical, it can also impart an extra kick, launching the surviving star at even higher speeds. This is exactly what may have happened to VFTS 102. When its companion exploded, the system likely unraveled. And whether from the orbital momentum or the shockwave itself, or both, VFTS 102 was cast out like a cosmic projectile. Its current speed through space is a relic of that ancient disruption, a motion that tells us, even millions of years later, that something shattered behind it. But the runaway nature of VFTS 102 doesn't just give us clues about its past, it also affects its future. Because it's moving so fast, VFTS 102 will eventually leave the star-forming region it was born in. It's not just running, it's escaping. Over time, it will drift into less crowded, more isolated regions of the galaxy, possibly living out its final days far from where it began. This exile will change what happens to its remnants as well. When it eventually dies, likely in a spectacular explosion of its own, it may not contribute its materials to the dense stellar nursery it came from. It may seed interstellar space somewhere else entirely, enriching a quiet region with the ashes of a star born in chaos. There's also the chilling idea that VFTS 102 isn't alone in its flight. If its companion left behind a neutron star or pulsar, then that object, too, would have been launched in the opposite direction, like the second half of a broken slingshot. Somewhere in the same region of the Tarantula Nebula, there may be a faint, fast-moving compact object speeding away from the same explosion, tracing a mirrored path across the galaxy. If we could locate that neutron star and match its motion with VFTS 102's, we would have even stronger evidence that the two were once gravitationally bound, a binary pair split apart by death. Runaway stars also help astronomers understand the dynamics of galaxies on a larger scale. Because of their high velocities, they can leave star-forming regions and enter quieter zones, where they act like beacons or test particles. They allow scientists to map stellar feedback, the way stars inject energy, matter, and motion into their environments. In this way, VFTS 102 isn't just a mystery, it's a tool. A fast, spinning, high-mass probe moving through space, changing everything in its wake. The violent motion of VFTS 102 is even more impressive when you consider that it hasn't been slowed down. Despite its mass and brightness, despite friction with interstellar dust and interactions with magnetic fields, it's still tearing through the cosmos at a velocity that challenges our expectations. That enduring speed reinforces the idea that the force that launched it was not gentle. It was explosive, perhaps even lopsided. And it left behind a star that will never return to where it began. In a universe governed by gravity, where everything is drawn together, slowly falling inward. The idea of a star escaping is both rare and deeply evocative. VFTS 102 is like a spark flung from a dying fire, a traveler born of destruction. Its motion is a message. It tells us that stars remember their histories. They carry the imprints of violence and chaos across the vacuum, even long after the explosions that shaped them have faded into silence. We see it now, blazing in the Tarantula Nebula, but it's already on its way out, driven by the ghost of a supernova, bearing both the memory and the momentum of an ancient, intimate catastrophe. In the chaotic afterglow of the supernova that may have torn its binary system apart, VFTS 102 was left spinning like a cosmic top, hurling through space as a runaway star. But even as it races forward, the memory of its past may still linger close behind, in the form of a ghost. Not a phantom in the traditional sense, but a celestial remnant, a neutron star or pulsar, the shattered, ultra-dense core of its long-lost companion. This hypothetical object, silent, compact, and cold, could be the last surviving trace of the violent event that made VFTS 102 what it is today. A neutron star is what remains after a massive star ends its life in a core-collapsed supernova. When the core of a star above roughly 8 solar masses exhausts its nuclear fuel, gravity wins the final battle, compressing the core to an object just 10 to 20 kilometers across, but with more mass than the Sun. The result is one of the densest forms of matter in the known universe. A single teaspoon of neutron star material would weigh around 1 billion tons on Earth. These exotic corpses don't shine brightly like stars. They emit weakly, often detectable only in radio waves or X-rays. And if they spin rapidly and beam radiation from their magnetic poles, we call them pulsars. Astronomers suspect that somewhere near VFTS 102, one such object may lie in hiding, a faint, fast-moving neutron star, flung in the opposite direction when the supernova exploded. Like VFTS 102, it would have been ejected by the sheer violence of the event. The gravitational bond between the stars would have shattered, and both remnants, the neutron star and the still-living VFTS 102, would have shot away from each other at tremendous speeds, never to reunite. If we can locate this companion's remnant, it could offer definitive proof of VFTS 102's binary past. What makes this even more compelling is that the region surrounding VFTS 102, the 30 Doradus Nebula in the Large Magellanic Cloud, is rich in supernova remnants, young pulsars, and neutron stars. The environment is active, noisy, and full of leftover debris from the deaths of massive stars. This means that while the possible companion remnant would be difficult to isolate among the background noise, it's not an unreasonable place to find such an object. In fact, searches are ongoing, using high-resolution imaging and radio observations to scan for any neutron star candidate moving in a path that mirrors VFTS 102's, just in the opposite direction. Finding that remnant would be more than just a cosmic coincidence. It would be a forensic discovery, like uncovering a broken chain with both ends still present. One end, VFTS 102, is hot, spinning, and massive. The other would be small, dim, and cold. But both would share a common trajectory, retraceable to a single point in space and time, the moment of their shared explosion. That convergence point would be the site of the supernova, the place where two lives were split apart, their fates diverging like shrapnel from a celestial bomb. There's even some precedent for this kind of discovery. Astronomers have identified binary systems where a neutron star or pulsar exists alongside a fast-spinning massive star, or where one object is missing, but the dynamics clearly hint at a past interaction. These systems are rare, but they're real. They are the relics of stars that refuse to evolve in solitude. And VFTS 102, for all its uniqueness, might fit squarely within this rare category. The presence of a nearby neutron star would also offer a new opportunity to date the event. Pulsars act like clocks. Their rotation slows predictably over time. If a pulsar can be identified near VFTS 102, and its age determined based on its current spin rate and energy loss, astronomers could potentially pinpoint the exact age of the supernova, and therefore the timeline of VFTS 102's transformation. This would help calibrate models of mass transfer, angular momentum gain, and even how fast stars can realistically spin after such events. But for now, the companion remains a mystery, a ghost, unseen but suspected. It's out there, perhaps drifting quietly through the same nebula that once hosted their shared origin, or already moving into the galactic outskirts, a silent witness to a partnership broken by death. And even if we never find it, if it's too faint, too far, or too hidden in the nebular glow, it doesn't matter. Because VFTS 102 carries its memory in every measurable property. In its velocity. In its spin. In the strange chemical traces on its surface. In the fact that it shouldn't exist the way it does, unless something extraordinary, something catastrophic, happened. In that sense, the ghost of its companion lives on inside VFTS 102. It is not just a fast star. It is the living half of a stellar story, a remnant of a binary past carved in rotation, trajectory, and silence. The story of VFTS 102 doesn't end with its violent past. In many ways, that's just the prologue. What followed the supernova, the ejection, and the presumed death of its companion was a transformation unlike anything we typically witness in the life of a star. VFTS 102 didn't just survive. It didn't simply carry on. It was reborn, rejuvenated in every sense of the word, reshaped by the chaos it endured into something far more massive, volatile, and extreme than what it was before. This was no gentle evolution. This was a metamorphosis forged in the fires of destruction. VFTS 102, once the secondary in a binary, emerged from this process as a reborn monster. Massive stars already live on the edge of physical balance. Gravity pulls inward, fusion pushes outward. Even slight shifts in that equilibrium can have enormous consequences. But when a star is fed additional mass from a companion, especially through a runaway process like Roche lobe overflow, it begins to behave in ways that challenge our models. Its temperature increases, its outer layers become turbulent, and perhaps most critically in VFTS 102's case, its rotation accelerates to extreme limits. This process didn't just rejuvenate the star. It rewrote its fate. To understand the nature of this rebirth, we have to consider what VFTS 102 may have been before the mass transfer. It was likely already a massive star, perhaps 15 to 20 times the mass of the Sun. But the influx of matter from its companion pushed that figure much higher, ballooning it to what astronomers now estimate is around 25 solar masses. That increase doesn't seem massive on paper, just 5 to 10 more suns. But in the delicate dance of stellar physics, it's enough to push a star into a completely different evolutionary track. It's enough to raise its core temperature, alter its internal mixing, and most importantly, shave millions of years off its lifespan. It's like pouring gasoline on a fire that was already burning white-hot. The metaphor of a reborn monster is not just poetic, it's quite literal. This star, which may have otherwise lived a relatively stable, if still dramatic, life, was converted into something more unstable, more dangerous, and more mysterious. Its equatorial velocity, already high from its initial formation, was now magnified by the angular momentum it absorbed from the accretion disk. It became what we call a critically rotating star, spinning so close to its structural limits that even a slight increase in speed could cause it to start shedding its mass. The difference between stability and chaos is razor thin. And VFTS 102 walks that edge with every passing moment. What's fascinating about this process is that it's not unique to VFTS 102, but it is taken to the most extreme in its case. Rejuvenation through mass transfer is a well-known concept in stellar astrophysics. In fact, it's one of the leading explanations for blue straggler stars, which are found in old clusters where most stars have aged and cooled, yet a few seem oddly hot and young. These blue stragglers are thought to have been refreshed by mass from a now vanished companion, effectively resetting their evolutionary clocks. VFTS 102 may be one of the most massive, fastest, and most extreme examples of this phenomenon ever observed. And the evidence for this is etched into its very spectrum. The star doesn't look like it belongs among others of its apparent age. Its temperature, luminosity, and chemical composition all point to a star that has been infused with new energy. It is hotter than it should be, and its outer layers bear the scars of a turbulent mixing process, a churn of older and younger materials brought together in a way only mass transfer can explain. This rejuvenation also complicates efforts to determine the star's true age. Stellar age estimation typically depends on comparing a star's temperature and luminosity to models of stellar evolution. But those models are built on assumptions of isolated, undisturbed development. VFTS 102 has thrown those assumptions out the window. Because of the mass it gained and the energy it absorbed, it appears younger than it likely is. It's a kind of cosmic Botox, resetting the surface clock while hiding the deeper history underneath. But rejuvenation has a price. The increased mass and velocity make VFTS 102 far more prone to instability. It is more likely to experience violent outbursts, to shed material into space through rapid stellar winds, or even to lose angular momentum in unpredictable ways. Its interior is a cauldron of pressures and temperatures so intense that even slight perturbations could trigger sudden shifts, possibly hastening its collapse. In fact, its entire life expectancy has now been shortened. Whereas a star of 15 solar masses might live for 10 million years, a star of 25 solar masses like VFTS 102 might only survive for 6 to 7 million years, and possibly less, given its near-critical rotation. And remember, it's already partway through that journey. This means that VFTS 102 is a ticking clock. It is hurtling toward a cataclysmic end, its future written not in centuries or millennia, but in cosmic moments. And when it dies, it may do so in one of the most violent and energetic ways possible for a star, a long-duration gamma-ray burst. This type of explosion, among the most powerful events in the known universe, requires a star with high mass, low metallicity, and fast rotation, all boxes that VFTS 102 ticks. If it collapses directly into a black hole while maintaining its angular momentum, it could launch relativistic jets from its poles, releasing more energy in seconds than the Sun will emit in its entire 10 billion year life. That's the legacy of this reborn monster. Not peace. Not stability. But extremity, from beginning to end. From a tight binary system, to a violent explosion, to runaway acceleration and chaotic motion, to the verge of tearing itself apart, VFTS 102's entire identity has been shaped by upheaval. It is a survivor, yes, but more than that, it's an inheritor. It has absorbed the essence of its companion and become something more, something stranger, something more unstable than either star alone could have ever been. And all of this is happening now, as we speak. Light from VFTS 102 is still racing across the void toward us, revealing flickers of this extraordinary history. With every new observation, we learn more about what happens when stars are reborn through destruction, when stellar life is reshaped by stellar death. It's a chilling thought, that the most powerful version of a star might not be the one it was born to be, but the one it becomes after losing everything. The spin of a star is not just a detail, it's a defining feature. For VFTS 102, spin is its identity, its power, and its downfall. In the vast and intricate language of stellar physics, rotation is a force that rewrites the rules, bending the natural flow of a star's life from the inside out. It's easy to imagine rotation as a superficial motion, like the twirl of a planet or the spin of a wheel. But in the realm of astrophysics, especially when it comes to massive stars, rotation is a fundamental physical influence, affecting nearly every single property a star possesses: its shape, its temperature, its magnetic field, its winds, its internal structure, its lifespan, and ultimately, the way it dies. To start with, rotation alters the shape of a star. Most people envision stars as perfect spheres, but that's only true if the star is not rotating, or rotating very slowly. When a star spins rapidly, centrifugal force acts strongest at the equator, pushing outward and resisting the star's own gravity. This flattens the poles and causes the equator to bulge. The result is a shape known as an oblate spheroid, wider across the middle, flatter at the top and bottom. VFTS 102, spinning at around 600 km per second, has taken this to the extreme. Its equator bulges so dramatically that its overall structure deviates from standard models. This distortion isn't just cosmetic, it has serious implications for the rest of the star's properties. One of those implications is gravity darkening. Because the star is stretched at the equator, the surface gravity there is weaker. Weaker gravity means less compression, cooler temperatures, and lower luminosity. Meanwhile, the poles, where gravity is stronger due to the lack of centrifugal push, remain hotter and brighter. This means that VFTS 102 emits more light and heat from its poles than from its equator. It's a phenomenon that makes its surface highly asymmetric in both temperature and radiation. The star, from a distance, glows unevenly, like a beacon whose brightness wobbles as it spins. And because it's spinning so fast, it completes a rotation every day or two, creating a rapidly changing stellar environment. Rotation also impacts a star's internal mixing. In non-rotating stars, fusion occurs in the core, and the resulting elements remain mostly trapped there. But in fast rotators, the centrifugal force and turbulence created by spin stir the stellar interior. This leads to chemical mixing, which brings fresh hydrogen into the core and circulates fusion products like helium and nitrogen to the surface. This affects both the star's observed spectral features and its lifespan. More fuel in the core might mean more time for fusion to continue, but the same process that mixes the material also increases the rate of fusion, burning that fuel faster. The net result is that fast-rotating stars like VFTS 102 live fast and die young, consuming their lives in a blaze of chaotic, energetic reactions. But the influence of spin doesn't stop there. It affects the star's stellar wind, the stream of charged particles that flow outward from its surface. Fast rotation can cause equatorial mass loss, where the outer layers begin to peel away from the star's midsection. In extreme cases, like those approaching critical rotation, as VFTS 102 is, the centrifugal force becomes so great that the star starts to eject material in a disk-like structure around its equator. These stars often become B-stars, surrounded by a glowing disk of gas formed from their own expelled matter. While VFTS 102 hasn't yet shown a persistent disk, the potential exists. Its rotational speed is right at the edge, and even minor perturbations could trigger shedding events. Spin also plays a crucial role in a star's magnetic field. In theory, rotation should enhance magnetic dynamo effects, creating powerful, organized magnetic fields. But here's where VFTS 102 throws yet another wrench into the model. Despite its velocity and mass, observations have shown little to no magnetic field. This is a puzzle still being explored. One theory suggests that its internal structure, altered by extreme spin and mass transfer, may suppress magnetic generation. Another possibility is that its magnetic field is present but tangled and weak at the surface, hidden from current detection methods. Regardless, the absence of a strong field in such a fast rotator challenges assumptions and forces scientists to rethink how stellar magnetism is generated. And then there's the biggest question of all: how does spin affect how a star dies? For a star like VFTS 102, this is where things become truly dramatic. Massive stars already die explosively, collapsing under their own gravity and releasing immense amounts of energy in supernovae. But if the star is rotating rapidly when it collapses, especially if it retains that angular momentum until the end, it can lead to a phenomenon far more violent: the formation of collapsars and gamma ray bursts. Here's how it might unfold. As VFTS 102 exhausts its fuel, its core will collapse inward. But if it's spinning fast enough, the collapse won't happen symmetrically. Instead, matter will spiral inward along the rotational axis, while energy builds at the poles. Under the right conditions, this can lead to the formation of relativistic jets, beams of matter and energy traveling near the speed of light, piercing through the outer layers of the star and erupting into space as gamma ray bursts. These bursts are short-lived, but their impact is colossal. A single long-duration gamma ray burst can release more energy in 30 seconds than our Sun will emit in 10 billion years. Only a small fraction of massive stars become gamma ray burst progenitors. Most lose their rotation long before death, or explode in other ways. But VFTS 102 is different. It's retained its spin. Its mass is high, its metallicity is low, and its motion is unimpeded. If it holds together, if it doesn't shed too much mass or lose its momentum, It is a prime candidate to end its life in one of the most spectacular explosions the cosmos has to offer. So why does spin matter? Because it rewrites the fate of a star. It bends its light, warps its shape, changes its chemistry, accelerates its death, and reshapes its legacy. For VFTS 102, spin is the architect of its past and the executioner of its future. Without that spin, it would be just another massive star in a crowded nebula. With it, it is one of the most extreme, mysterious, and dangerous stars we've ever found. It's not just spinning, it's transforming every second, evolving at a pace that defies normal stellar timelines. And somewhere in that motion is a countdown, ticking quietly, invisibly, toward a conclusion we can barely begin to imagine. VFTS 102 isn't just a star spinning fast, it's a star speeding toward a violent end. It lives in a state of delicate balance, with its enormous mass pressing inward and its extreme rotational speed pulling outward. Every second, this tension plays out inside its core, as nuclear reactions fight against gravity, and rotation distorts its shape and structure. But this balance won't last forever. The clock is ticking, and when it runs out, VFTS 102 may not simply explode, it could detonate with such force that it lights up the cosmos in one of the most powerful events the universe can produce. A long-duration gamma-ray burst. Gamma-ray bursts, or GRBs, are the brightest and most energetic explosions known. They are short in time, sometimes lasting just a few seconds, but in that fleeting window, they release more energy than the sun will emit over its entire 10 billion-year life. And there's a particular type of GRB, the long-duration kind, that has been traced back to massive, rapidly rotating stars that collapse into black holes. VFTS 102 fits that profile with eerie precision. Let's look at what makes a star capable of producing such an event. To create a long-duration GRB, a dying star needs to satisfy several key conditions. First, it must be massive enough to collapse into a black hole rather than forming a neutron star. VFTS 102, at around 25 solar masses, easily clears that bar. Second, it needs to retain its rotational momentum as it collapses. This is critical. Without the spin, the star can't channel its energy into the twin polar jets that define a GRB. Most massive stars lose their spin through stellar winds and magnetic braking as they evolve, but VFTS 102 is different. It has somehow preserved its extreme spin all the way into its current stage, and if it holds onto that speed until the end, it may collapse in a way that channels that angular momentum into violent, focused energy. Third, the star must have low metallicity. This may sound counterintuitive, but it's crucial. High metallicity stars, those with more elements heavier than hydrogen and helium, tend to lose mass rapidly through powerful stellar winds. These winds carry away not just material but angular momentum, gradually slowing the star down. But VFTS 102 is located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way that has lower metallicity than our own. This means VFTS 102 is less prone to strong mass loss, allowing it to maintain its rapid spin across millions of years, another critical factor in making a GRB possible. When the time comes, VFTS 102 will exhaust its nuclear fuel. The fusion in its core, now fusing heavier elements like carbon, oxygen, and silicon, will no longer be able to support the intense gravitational pressure. The core will collapse. Under the crushing force of gravity, it will shrink past the neutron star phase and become a black hole. If enough rotational energy remains, the infalling matter will not fall in quietly. It will form a spinning, high-energy accretion disk around the forming black hole, and from the poles of this disk, relativistic jets, beams of matter and gamma radiation, will shoot outward. These jets are the gamma-ray bursts. But the mechanics are far from simple. As the core collapses, the jets must burrow their way through the star's outer layers. If they don't escape before the star implodes or collapses in on itself entirely, no GRB is visible. The process must be incredibly fine-tuned. But if the jets are fast and powerful enough, moving near the speed of light, they can pierce through the surface and erupt into space in a brief but apocalyptic flash of gamma radiation. This blast can outshine the entire host galaxy. It can ionize planets across light years of distance. It can leave behind an expanding shockwave that rips apart anything in its path. These events are rare, partly because the conditions are so precise. But the moment astronomers discovered VFTS 102, and especially once its rotation was measured, it became clear that this star is a prime candidate to become one of them. It's like a coiled spring, a cosmic warhead in slow motion. It has the mass. It has the rotation. It has the environment. All that's missing is time. This looming possibility isn't just academic. Gamma ray bursts are not only important in terms of cosmic energy, they're also life-altering, quite literally. A nearby GRB could destroy a planet's ozone layer, unleashing lethal radiation onto the surface and triggering mass extinctions. Fortunately, VFTS 102 is located far enough away in the Large Magellanic Cloud to pose no direct threat to Earth. But its future explosion will be visible to us. If the jets are oriented even remotely in our direction, we could witness the GRB with satellites in orbit, detecting its signal across vast intergalactic distances, a message from a dying star spinning into oblivion. What happens after such an explosion? The star collapses fully, forming a black hole, and the jets fade. What remains is a silent void where a star once spun at nearly impossible speeds. The surrounding nebula would be filled with high-energy particles, expanding gas, and possibly relativistic shockwaves, all pushing outward and enriching the environment. This new material might one day help form new stars, seeding future generations with elements forged in the final heartbeat of VFTS 102. And that's the ultimate irony. This incredibly violent death may give rise to new life elsewhere in the cosmos. It's rare for astronomers to see the precursors of a GRB before it happens. Most of the time, we only detect the aftermath, a dying star's final scream across the electromagnetic spectrum. But with VFTS 102, we may be watching a ticking gamma-ray bomb as it slowly spins toward its doom. Every rotation brings it closer to that inevitable collapse, to the moment when its mass, spin, and structure can no longer hold. And when that moment comes, it won't just fade into the dark, it will tear a hole in the sky, shouting its death across millions of light years. VFTS 102 is a star that, by every known metric, should not exist the way it does. It is the product of destruction, running from its past, fueled by chaos, spinning at the brink, and hurtling toward a spectacular demise. It is not just a star with a violent end, it's a star whose entire existence is a slow-motion catastrophe, one that will climax in a cosmic blast that will echo for eons. To understand the full magnitude of VFTS 102's likely fate, we must turn to the most violent death in the known universe, the long-duration gamma-ray burst. These events are not just explosions, they are cataclysms, ripping through space-time with such force that their energy can be felt across galaxies. They are rare, unpredictable, and unfathomably powerful. And the terrifying truth is that VFTS 102 might be one of their future progenitors. If it is, then it is destined not to go quietly, but to unleash the ultimate stellar scream, a burst of gamma radiation that could release in mere seconds more energy than our sun will emit in 10 billion years. To grasp the magnitude of that, imagine compressing every photon, every heat wave, and every nuclear reaction our sun will ever generate, from its first flicker of hydrogen fusion to its last breath as a white dwarf, into a single, blinding moment. That's the scale of a gamma-ray burst, or GRB. Now imagine that moment happening in two narrow, focused beams of unimaginable energy, each traveling across the cosmos at the speed of light. That's not a supernova. That's something far worse. Long-duration GRBs, as the name suggests, last more than 2 seconds, often stretching up to several minutes. They are usually associated with the collapse of massive stars, especially those that rotate rapidly and possess relatively low metal content, exactly the kind of star VFTS 102 is. In fact, the model that explains these events is sometimes called the collapsar model, short for collapsing star. In this model, when the star's core runs out of nuclear fuel, it can no longer resist gravity and collapses inward to form a black hole. If the star is spinning rapidly, as VFTS 102 is, then the material falling into the black hole forms a dense, hot, swirling accretion disk. From this violent engine, Twin jets of energy are launched along the poles of the star, carving through its outer layers and shooting out into space at nearly the speed of light. But here's the critical part: for the gamma ray burst to be visible, these jets must successfully break out of the collapsing star's surface and be oriented in such a way that at least one is aimed in our direction. If they fail to escape, or are directed elsewhere, no GRB is observed, though the black hole still forms. That means even among the rare stars capable of producing GRBs, only a tiny subset are seen by us. Yet even that fraction has yielded hundreds of detections, each one a titanic event that instantly becomes the brightest object in the sky from its location. The energy output of a GRB is staggering. A typical long-duration GRB emits something on the order of 10 to the power of 44 joules of energy in its prompt phase. That's not just more than the Sun, it's more than all the stars in an entire galaxy emit in the same time frame. For a few heartbeats, that one collapsing star can outshine a billion suns. And yet, that's just the beginning. After the initial burst of gamma radiation comes the afterglow. As the relativistic jets slam into the surrounding interstellar material, they create shockwaves that emit X-rays, ultraviolet radiation, optical light, radio waves, and more. This afterglow can last for hours, days, even weeks, allowing astronomers to study the event in extraordinary detail. These observations have helped scientists piece together the structure of the jets, the composition of the progenitor star, and the environment surrounding the explosion. If VFTS 102 becomes a GRB, and if we're lucky, or perhaps unlucky, enough to be aligned with one of its polar jets, we would detect a sudden, intense flash of gamma rays in our orbiting observatories like NASA's SWIFT or Fermi Gamma Ray Space Telescope. There would be no warning. The burst would appear, last a minute or so, and vanish. But the data gathered in that minute could unlock volumes of insight into the physics of collapsing stars, jet formation, and black hole birth. Let's not forget, gamma rays are the most energetic form of electromagnetic radiation. They are far more powerful than X-rays, capable of ionizing atoms and breaking molecular bonds. Fortunately, Earth's atmosphere blocks gamma rays, which is why we rely on satellites to detect them. Still, the sheer intensity of a GRB aimed at a planet could have devastating consequences. If such an event happened close enough, within a few thousand light-years, it could strip away an atmosphere, wipe out life, and cause a mass extinction. Some scientists even hypothesize that a GRB may have been responsible for one of Earth's past extinction events. Thankfully, VFTS 102 resides in the Large Magellanic Cloud, about 160,000 light-years away. That's far enough that any GRB it might produce wouldn't directly harm Earth, but it's close enough that we would receive a clear signal, one of the brightest gamma-ray flashes we'd ever detect. It would be a landmark moment in astronomy, witnessing a star we had already studied in detail detonate into a gamma-ray burst, confirming decades of theory and tying together our understanding of mass, spin, stellar death, and black hole formation. It's strange to think that such violence could be so scientifically valuable. But in truth, GRBs are laboratories in the sky. They allow us to study conditions that can't be replicated on Earth, densities, temperatures, and magnetic fields that exist only in the most extreme corners of the cosmos. And they serve as cosmic lighthouses, shining across billions of light-years to illuminate the early universe. Some of the farthest objects ever detected are GRBs, helping us map the formation of the first stars and galaxies. In that sense, VFTS 102 is not just a dying star, it is a potential key to understanding the evolution of the universe. Its final act may not just end its life, but open a new chapter in ours, revealing how massive stars collapse, how black holes are born, and how energy can be unleashed on a scale we can barely comprehend. It will happen suddenly, without warning. One day, perhaps thousands of years from now in its local frame, or already in our past, with the light still racing toward us, VFTS 102 will collapse. And in that moment, it will fire off a gamma-ray burst, the ultimate death cry of a cosmic monster. It will vanish, leaving behind a black hole and a shockwave that expands into the cold darkness. And we will know, for one brief moment, that we witnessed the death of a star at the very edge of nature's limits, not through silence, but through fire and light that reached across space to whisper its end. As the final curtain draws nearer for VFTS 102, the mechanics of its death spiral into something more than collapse, something more than explosion. This is a star not destined for a quiet end, nor a drawn-out death. It is a star careening toward oblivion, and it is spinning as it goes. With every rotation, with every second that passes, its core creeps closer to instability. And when that final moment comes, VFTS 102 may not go supernova in the traditional sense. Instead, it might skip straight to the endgame, collapsing directly into a black hole, launching high-energy jets through its poles like blades through the fabric of the universe. For most massive stars, the death sequence begins when nuclear fusion in the core ceases. As lighter elements like hydrogen and helium are burned into heavier ones like carbon and oxygen, the fusion process generates enough outward pressure to resist the crushing pull of gravity. But this balance is fragile. Once iron begins to form in the core, a dead end for fusion, the internal engine stalls. Gravity then takes over, causing the core to collapse inward at incredible speed. But in the case of VFTS 102, this process may be dramatically altered by its extreme rotation. Instead of simply imploding into a neutron star, the momentum built up by its relentless spin could tip the collapse into a different path altogether. The core may collapse directly into a black hole, bypassing the neutron star phase entirely. This is what astrophysicists refer to as a collapsar, a massive star whose death doesn't leave a glowing remnant, but a gaping void of gravity and silence. But VFTS 102's rotation adds a twist, literally. When such a fast-spinning star collapses, not all the infalling material can plunge directly into the black hole. The angular momentum causes matter to whirl around the newly formed singularity, forming an accretion disk, a dense, hot, spiraling ring of gas that feeds the black hole in a process of furious self-destruction. This disk is no gentle ring. It is a zone of unimaginable density and temperature, where friction, magnetism, and radiation battle in a storm of exotic physics. And here's where the spectacle begins. As the material in the accretion disk spirals in, magnetic fields twist and amplify, channeling energy into the star's rotation axis. If enough energy builds, and if the core collapses fast enough to trap the pressure, the result is a pair of relativistic jets, high-energy beams of plasma and gamma radiation fired at nearly the speed of light from the star's poles. These jets are narrow, focused, and devastating. They are the same jets that form a gamma-ray burst, but even beyond their initial flash, they signal the star's final unraveling. VFTS 102, because of its rotational structure, would funnel these jets directly along its spin axis, aligned with the very rotation that defined its life. This symmetry is no accident. It's a result of conservation laws, angular momentum, magnetic field topology, and the directional mechanics of gravitational collapse all collaborate to aim the final blast along the axis that has defined the star's shape, surface, and destiny. Once launched, these jets can slice through the star's outer layers in seconds. They carry with them particles traveling at nearly the speed of light, intense magnetic fields, and raw energy that can outshine an entire galaxy. They may emerge from the star's surface in under a minute, flashing across the electromagnetic spectrum. And then, nothing. No visible star. No lingering supernova shell. Only the jets, fading into space, and a black hole spinning silently at the core. This collapse is not just an end. It's a transformation. The matter that once made up the star, the hydrogen that fused into helium, the elements stirred by convection, the atoms formed over millions of years, has become part of a singularity. In a flash, VFTS 102 will go from a visible, pulsing engine of light to an object from which not even light can escape. Its immense gravity will warp spacetime, pulling in anything that drifts too close. And the mass that once gave birth to starlight will become a well of pure gravity. But even as it vanishes, VFTS 102 will leave a signature, a mark that says, "I was here, and I died spectacularly." The afterglow of its jets will linger, revealing clues about its composition, its velocity, and the environment it destroyed on its way out. Observatories may detect the faint echoes of this collapse for days or even weeks, reading its final messages across X-ray, ultraviolet, and radio wavelengths. Scientists will sift through the data, piecing together the story of a star that spun itself to death. What makes this so fascinating is how intertwined spin and collapse have become. Without its rotational speed, VFTS 102 might still die dramatically, but it would not become what it's poised to be, a relativistic engine of cosmic death. It is its rotation that enables the jet formation, that guides the accretion disk, that ensures the collapse is not just inward, but directed. It spins into oblivion, and in spinning, it carves a path to an end that few stars can reach. And even beyond the moment of collapse, its spin will persist. The black hole it leaves behind will carry the rotational momentum of its predecessor. It will be what's called a Kerr black hole, a rotating singularity with frame-dragging effects so powerful that it twists the very fabric of spacetime around it. If you were to orbit such a black hole, you would be pulled not just inward, but around, dragged by its spin. The imprint of VFTS 102's life will survive in the most alien form of all, as a twist in space itself. So when we say VFTS 102 will spin into oblivion, we don't just mean metaphorically. We mean it literally. Its death will be governed by its motion. Its collapse will be accelerated by its velocity. Its aftermath will be shaped by the angular momentum it never let go. This is not just a star ending, it is a cosmic ballet, a dance of matter, energy, and gravity performed at the very edge of physics. VFTS 102 began its life in violence, likely born of binary chaos and supernova trauma. It evolved in a state of high tension, spinning faster than almost any star ever recorded. And it will die in perfect symmetry, a collapse shaped by the same spin that once defined its uniqueness. As it vanishes, the universe will bear witness. Not because the star was massive, not because it was bright, but because it did something few stars do. It spun itself into history, into legend, and finally into nothing at all. While the interior of VFTS 102 is a crucible of nuclear fusion and angular momentum, its surface is no less dramatic. In fact, the outermost layers of this star are likely a realm of constant upheaval, a place of roaring stellar winds, tangled streams of plasma, and unimaginable turbulence, all driven by its astonishing spin. If we could somehow hover safely above the star's surface, we wouldn't see calm, glowing starlight. We'd witness an apocalyptic hurricane of stellar proportions, a sea of incandescent chaos, stirred to extremes by centrifugal force. This turbulence isn't just theoretical. Scientists understand that as a star approaches its critical rotation speed, where centrifugal force nearly balances gravity, the equilibrium of the outer layers becomes unstable. VFTS 102 spins at around 600 km per second, just shy of that critical threshold. That means the plasma at its equator, already stretched thin by the star's oblateness, is on the verge of breaking free. The gravitational hold weakens, the pressure gradients increase, and surface material becomes wildly mobile. We are talking about gases so hot and energetic that atoms are stripped of electrons, creating a glowing soup of ionized particles, constantly in motion. One effect of this is the generation of stellar winds far more powerful than those found on average stars like our Sun. In our solar system, the Sun's solar wind drifts outward at about 400 to 800 km per second, driven by magnetic activity and coronal heating. But VFTS 102, with its intense luminosity, high surface temperatures, and rotational distortion, likely unleashes stellar winds moving at thousands of kilometers per second. These winds blow unevenly across the surface, being stronger near the poles, where gravity is higher and material is more tightly bound, and weaker at the equator, where centrifugal forces counteract gravity. The result is not a uniform outflow of gas, but a chaotic, asymmetric spray of plasma, surging into the surrounding space. This motion gives rise to structures that resemble tornadoes or vortices, but on a scale so vast and violent they defy earthly comparison. Imagine whirlpools of gas larger than entire planets, spiraling across the surface, feeding on the pressure differences between the poles and equator, writhing and shifting every second. These so-called stellar tornadoes aren't made of air, of course, They're composed of superheated plasma, moving through magnetic field lines, twisting and warping space as they go. In regions where the surface layers are particularly unstable, this turbulence may give rise to localized mass ejection events, where chunks of the star's outer envelope are flung outward into orbit. This is one of the mechanisms thought to contribute to circumstellar disks around B stars, rapid rotators that, like VFTS 102, can hold on to all their mass. Though VFTS 102 hasn't been definitively observed with a persistent equatorial disk, the theoretical groundwork is there. It sits right at the edge of mass shedding, and any minor increase in rotational speed, or shift in internal equilibrium, could tip it over that edge. Adding to the surface mayhem is the presence of differential rotation. Just as Earth's equator spins faster than its poles, stars can exhibit this behavior too. In such cases, different latitudinal bands of the star rotate at different speeds, causing shear forces across the surface. These forces tear through plasma like rip currents, creating turbulence zones, shock fronts, and heat differentials that drive even more instability. In VFTS 102, the extent of this differential rotation is not yet fully known, but given its extreme parameters, it's highly likely the outer layers are ripping across themselves, forming eddies and cyclonic structures that dwarf even the most violent storms in the known universe. There's also the matter of convective motion. In some massive stars, energy is carried from the core to the surface through convection, columns of hot plasma rising while cooler gas sinks. Combined with rapid spin, this convection can be twisted into helical flows, spiraling arcs of material looping through the atmosphere of the star, dragging magnetic fields with them. These twisted fields can amplify and reconnect, triggering localized outbursts or flares. While VFTS 102 seems to lack a strong, coherent magnetic field, more on that mystery later, the turbulence and motion at the surface would still be energetic enough to drive bursts of radiation, flickers of brightness, or even temporary structural instabilities. In short, the surface of VFTS 102 is not a calm photosphere. It's a boiling sea of fire, churning under forces that push matter and energy to their limits. It's a place where tens of millions of degrees of heat meet thousands of kilometers per second of speed, where gravity barely wins the battle against centrifugal escape, and where light itself has to fight through storms of plasma to escape into the cosmos. If you could see it with your eyes, it wouldn't look like a star, it would look like a violent, glowing maelstrom, spiraling furiously in space, erupting with streamers of gas and shedding photons like sparks from a forge. Even the emission lines in its spectrum, the fingerprints of atoms and ions in its atmosphere, bear the hallmarks of this surface chaos. Instead of narrow, well-defined lines, astronomers observe broad and blended features, smeared by the Doppler effect of all that rapid motion. It's like listening to a symphony played on instruments that are being thrown around in a tornado, beautiful, but utterly disordered. All of this surface activity isn't just a side effect of VFTS 102's spin. It's a preview of what's coming. This turbulence, this barely contained chaos, is the friction at the edge of catastrophe. It shows us that VFTS 102 is teetering on the brink, not just in terms of mass or heat, but in terms of stability. The forces at play on its surface are trying to tear it apart, atom by atom, day by day. And when its time comes, it won't take much to push the star over that edge. In this way, the surface of VFTS 102 is not just a battlefield of gas and light, it is the star's most visible cry for help, a roiling testament to a life spent spinning too fast, burning too hot, and racing too close to destruction. In the turbulent, high-energy world of VFTS 102, one mystery stands out starkly, one that contradicts our most basic expectations about how stars work. Given its incredible rotational speed, its chaotic surface, and the violent processes churning inside it, astronomers expected to find something else, something that usually goes hand in hand with fast stellar rotation, a powerful magnetic field. And yet, VFTS 102 appears to be almost magnetically silent. This is strange. In stellar astrophysics, rotation is one of the key ingredients in magnetic field generation. It's a principle rooted in the stellar dynamo theory, the idea that, inside a star, the movement of charged plasma, combined with rotation and convection, creates a self-sustaining magnetic field. In stars like our Sun, this dynamo manifests in an 11-year sunspot cycle, magnetic field reversals, and solar flares. In more massive and faster rotating stars, magnetic fields can be even more intense, twisting their outer layers, funneling stellar winds, and producing spectacular flares or polar outflows. But VFTS 102? Despite spinning faster than any massive star we know, at a blistering 600 kilometers per second, it shows no clear signs of a strong magnetic field. This is not just unusual. It's perplexing. So what might explain this magnetic mystery? One possibility lies in the internal structure of VFTS 102. Unlike the Sun, which has a convective outer layer and a radiative inner layer, a configuration that supports the classical dynamo, many massive stars like VFTS 102 have radiative envelopes and only convective cores. This difference changes how, and whether, a magnetic field is generated and sustained. Without a thick convective zone near the surface, the traditional dynamo mechanism may not be efficient. So, even though the star is spinning rapidly, it might not have the right internal dynamics to generate a robust, large-scale magnetic field. However, this explanation isn't entirely satisfying. Some massive stars do manage to generate strong magnetic fields even with radiative envelopes. Moreover, even if a global dynamo isn't present, we'd still expect to find fossil magnetic fields, remnants from the star's formation, or fields amplified during previous mass transfer events, especially considering the violent, binary origin suspected in VFTS 102's past. Yet, spectral analyses and polarimetric studies show no evidence of the kind of magnetic strength we'd expect. This leaves scientists with another hypothesis, that VFTS 102's extraordinary spin rate may actually be inhibiting its magnetic field. How? Let's explore. One idea is that the centrifugal force from the rotation stretches the star's internal layers so much that it suppresses the large-scale convective patterns needed for dynamo action. Instead of enabling the magnetic field, the high spin rate might be disrupting the flows that generate it. The plasma in the core and near the equator could be too turbulent, too rotationally dominated, to allow coherent magnetic structures to form and persist. Imagine trying to form stable weather patterns in a hurricane spinning 100 times faster than normal. Any organized system is immediately shredded. Another possibility involves magnetic braking, a process where a star loses angular momentum due to the interaction between its magnetic field and its stellar wind. If VFTS 102 had a strong magnetic field in its earlier life, it should have lost rotational speed over time. But it didn't. It's still spinning at a near breakup speed. This suggests either that it never had a strong magnetic field, or that the field somehow collapsed or dissipated before it could slow the star down. Could its strange birth, possibly the result of a binary merger or a massive mass transfer episode, have disrupted its magnetic engine permanently? Adding to the mystery is the fact that some B stars, a class of rapidly rotating stars, like VFTS 102, also show weak or undetectable magnetic fields, despite their fast rotation and disk-like gas ejections. This suggests there might be a broader trend, one where extreme spin doesn't always equal strong magnetism, at least not in the way we usually expect. Of course, there's also the possibility that VFTS 102 does have a magnetic field, but one that is highly complex or small-scale, structured in such a chaotic way that it cancels itself out when observed from a distance. Just as Earth's magnetic field is primarily dipolar, but has smaller, local distortions, VFTS 102's field might be tangled, patchy, or multipolar, without a dominant orientation. This would make it difficult to detect with current techniques, especially given the star's extreme surface velocities and turbulent atmosphere, which can obscure or distort magnetic signals in spectroscopic data. Another speculative idea is that VFTS 102 is in a transitional magnetic state, perhaps between phases of field growth and decay. It's possible that the star's past interactions, especially if it once consumed a companion or merged with it, created temporary field structures that have since unwound or dissipated, leaving behind a magnetic void. This could also explain why the star's spin remains so high, it absorbed angular momentum from its companion without the accompanying magnetic feedback that would normally break that momentum over time. Regardless of the cause, the absence of a strong magnetic field in VFTS 102 poses a significant puzzle. Magnetic fields are supposed to be natural byproducts of rotation and plasma motion, yet here we have the fastest spinning massive star in recorded history, and it's not playing by the rules. This mystery has broader implications for astrophysics. It challenges our models of angular momentum evolution, mass loss, and magnetic braking. It suggests that rotation and magnetism, while deeply linked, may not always be as tightly coupled as we thought. And it raises new questions about how stars evolve under extreme conditions, questions that VFTS 102, in all its bizarre glory, may help us answer. If we can better understand why this star lacks a magnetic field, we may unlock new insights into how stars lose spin, how jets form, how gamma ray bursts are shaped, and how black holes inherit angular momentum. In short, this quiet magnetic anomaly might hold the key to some of the loudest, most violent processes in the universe. So, VFTS 102 spins furiously, rides with turbulence, teeters at the brink of collapse, and yet remains magnetically mute. It is a paradox, a star that should be a magnetic dynamo but instead spins in eerie silence. A riddle embedded in plasma, waiting for the right observations, the right theory, or perhaps a final explosion, to reveal the secret hidden in its missing magnetic heart. VFTS 102 may shine with unrivaled brilliance and spin at a velocity that defies comprehension, but in the grand scale of cosmic time, its life is barely more than a flicker. Like all massive stars, it lives fast, burns hotter than its smaller counterparts, and will die young. The same mass that grants it power is also its curse, dooming it to an existence that may last only a few million years, a cosmic sprint, not a marathon. To grasp just how short-lived VFTS 102 truly is, we need to understand the relationship between a star's mass and its lifespan. The larger a star, the more gravitational pressure builds at its core. That pressure fuels intense nuclear fusion, where hydrogen atoms are crushed into helium and later, heavier elements in a chain of processes that release staggering amounts of energy. This energy keeps the star from collapsing under its own weight, but it comes at a price. The faster the fuel burns, the shorter the star lives. Our Sun, for instance, is about 4.6 billion years old and is expected to continue shining for another 5 billion years or more. It fuses hydrogen relatively slowly, at a core temperature of about 15 million degrees Celsius. But VFTS 102, with a mass 25 times greater than the Sun, burns through its hydrogen like a wildfire through dry grass. Its core temperatures are much higher, possibly exceeding 50 million degrees, and the fusion reactions occur at a frenzied pace. Instead of billions of years, VFTS 102 may have a lifespan of just 5 to 7 million years total. It's likely already several million years into that life, middle-aged, or even approaching its end. This rapid aging is not visible in the sense we experience aging on Earth. VFTS 102 doesn't wrinkle or slow down. If anything, it grows hotter, denser, and more dangerous as time passes. Deep within, the nuclear reactions steadily change the star's chemical makeup, building up helium, ash, from the hydrogen fusion process. Eventually, when the hydrogen runs out in its core, the star will begin fusing helium into heavier elements like carbon and oxygen, progressing toward iron. Each new fusion stage is shorter and more violent than the one before it. The final moments, once fusion halts at iron, will occur in mere seconds. That's how fast a massive star can go from brilliance to obliteration. And while its interior races toward collapse, its outer layers continue to radiate power. The luminosity of VFTS 102 is thousands of times greater than the Sun. This means that even as it holds together against gravity and centrifugal force, it is blasting energy into the surrounding space. Much of this energy is carried away in the form of light and stellar winds, which strip mass from the star over time. In effect, the star is burning itself away from the inside and out, sacrificing its own structure in order to shine as brightly as it does. This level of mass loss can be immense. In its lifetime, VFTS 102 may shed several solar masses worth of material into space. These ejecta may feed the interstellar medium, help seed new stars, or even linger in the form of gas and dust shells. In the late stages of life, such massive stars often undergo violent outbursts, where massive eruptions cast off outer layers in brief but furious episodes of loss. These eruptions might not reach the scale of a full supernova, but they are like death throes, signals that the star is nearing its final act. There's also a poetic irony here: the more massive a star, the shorter its life. And the faster it spins, like VFTS 102, the more intense its fusion, the more chaotic its structure, and the more pressure it places on itself to evolve quickly. So while it may dominate its corner of the universe now, lighting up the Tarantula Nebula with scorching radiation and stellar wind, its time is running out. It may already be in a post-main sequence phase, or it could be teetering at the threshold, just one stage away from catastrophe. Unlike stars like the Sun, which die quietly and become white dwarfs, VFTS 102 will have no such gentle retirement. Its death will be sudden, violent, and final. A supernova, or more likely, a direct collapse into a black hole. But before that, there's still a little time. It continues to burn, to radiate, to spin furiously through its last stages of life. Astronomers are watching it closely, trying to catch hints of instability in its spectrum, subtle changes in its brightness, or fluctuations in the wind speed and mass loss rate, early warnings, if any can be found, of its imminent demise. But there is beauty in the brevity. The universe thrives on contrast, and stars like VFTS 102 are its extremes. In just a few million years, such stars create more complex elements, emit more energy, and influence their environment more profoundly than smaller stars do over billions of years. They are the forges of creation and destruction, catalysts for change in galaxies, initiators of shock waves and star formation, and the birthplaces of black holes and neutron stars. Their short lives are reminders of how cosmic influence is not measured by time lived, but by impact made. VFTS 102 may be young by stellar standards, but in its youth, it has already become a record breaker, a mystery, and a monument to what happens when the laws of physics are stretched to their limits. Its death will only add to that legacy. And so it races onward, bright, unstable, magnificent, toward an end that could happen at any moment in astronomical time. To the human eye, it may seem eternal. But in reality, it's already approaching the finish line, one fusion cycle at a time. Every photon it emits is a piece of borrowed time. Every flare, a whisper of what's to come. In this way, VFTS 102 is a paradox of scale, infinite in brightness, but finite in time. It is proof that even the most powerful things in the universe are fragile, ephemeral, and destined to burn out. To truly understand the power of VFTS 102's spin, we must first ask a simple but profound question: how do we know it spins that fast? After all, we're observing this star from across an entire galaxy, roughly 160,000 light-years away in the Large Magellanic Cloud. We cannot send probes to visit it, nor can we take a snapshot that shows it visibly rotating like a planet. Instead, the answer lies in one of the most powerful tools in the astronomer's arsenal, spectroscopy, a technique that lets us read the light of stars as if it were a detailed signature of their inner secrets. When we pass starlight through a spectrograph, it separates into a spectrum, a rainbow of colors that includes more than just visible light. Within this spectrum are thin, dark lines, called absorption lines, which occur when elements in the star's atmosphere absorb specific wavelengths of light. Each chemical element has a unique set of lines, like a barcode, and their position and shape tell us a great deal. But here's where things get interesting. If the star is not at rest, but is moving, those lines shift due to the Doppler effect. The Doppler effect, well known in sound waves, like the changing pitch of a passing siren, also applies to light. If a source of light is moving toward us, the wavelengths get compressed, blue shifted. If it's moving away, they're stretched, red shifted. But for a spinning star, one half of the star's surface is rotating toward us while the other is rotating away. This causes one side's light to be slightly blue shifted and the other's to be red shifted. The result isn't a simple shift, but a broadening of the absorption lines, a smearing effect across the spectrum that tells us how fast the star is rotating. For VFTS 102, astronomers used the Very Large Telescope, VLT, in Chile, one of the most powerful observatories on Earth, capable of gathering extremely faint and precise light from distant stars. By analyzing the spectral lines with high-resolution instruments, they found that the absorption features were incredibly broad, far broader than those of typical massive stars. When they modeled how fast a star would have to spin to cause that much line broadening, the number was astonishing, around 600 kilometers per second at the equator. This velocity isn't measured directly like watching a spinning top. It's inferred from how distorted the light becomes. That kind of rotational broadening is so extreme, it almost flattens the signature lines, making them blur into the surrounding light. In technical terms, this is known as rotational line broadening, and it's a highly sensitive diagnostic tool. The star's projected rotational velocity, often called v sin I, where I is the inclination angle of the star's rotation axis relative to us, is measured from the width of these lines. For VFTS 102, astronomers estimate that we're viewing the star close to equator, meaning we are looking at its rotation nearly from the side, not from the pole. This orientation gives us a nearly accurate measurement of the star's full equatorial speed. If we were seeing it from the pole, the rotational motion wouldn't show much Doppler shift, and the actual speed would be underestimated. But since the data matches what we'd expect from an edge-on view, the result is taken as close to the true rotation rate. Of course, measuring something this fast isn't simple. To be sure of their results, astronomers compared VFTS 102's spectrum with that of other massive stars in the same region, particularly those with known rotation rates. The difference was stark. Even among fast rotators, VFTS 102 stood out like a spinning blade. It didn't just edge past other stars in speed, it obliterated the curve. The fastest previously known stars spin at about 300 to 400 km/s. VFTS 102 practically doubles that. Further confirmation came from studying how the star's brightness and spectral features change over time. If a star is spinning rapidly, certain features, like temperature gradients, hotspots, and surface activity, can shift subtly as the star rotates. Though such variability is harder to detect in a distant star with no clear surface features, astronomers still examine line profile variations, looking for consistency with a rapidly rotating model. Everything checked out. But spectroscopy tells us more than just how fast the star is spinning. It also hints at how rotation changes the star's very nature. For example, in VFTS 102, the line shapes suggest gravity darkening, where the poles are hotter and brighter than the equator due to the star's oblate shape. That means the broadening is not just about spin, it's also a clue about temperature gradients, surface gravity variations, and more. The light is not only stretched by speed, it's shaped by physics. In short, spectroscopy allows us to measure the unseeable. It transforms the invisible forces of a distant star, its spin, temperature, and dynamics, into data we can analyze. Through this method, VFTS 102 went from being a faint light in the sky to a rotational record breaker. And in the process, it became something more than just a distant object. It became a window into stellar physics pushed to the absolute limit. There's a kind of elegance in that. We can't see the star's surface, can't hear its winds or feel its spin. But through its light, captured, split, and decoded, we can trace the motion of its atoms, the chaos of its storms, and the speed of its fall. Spectroscopy gives us the power to hear the song of the star's spin, even from across galaxies. In a universe filled with countless stars, each with its own story, structure, and secrets, there exists one that outpaces them all in terms of pure rotational velocity, VFTS 102. To this day, it holds the title of the fastest spinning massive star ever observed, and the more we study it, the more this record seems not only astounding but perhaps even unbreakable, given what we know about stellar physics. No other massive star on record reaches the dizzying rotational speed of VFTS 102. At approximately 600 km per second, the star's equator spins with such velocity that it approaches the very edge of what physics permits. For comparison, the second fastest spinning massive stars typically clock in at around 300 to 400 kilometers per second, still incredibly fast, but nowhere near the threshold that VFTS 102 teeters on. It's not just fast, it's in a league of its own, practically rewriting the upper limit of what we thought was possible for stellar rotation. To understand the magnitude of this record, let's put it into further context. Stellar rotation isn't a rare phenomenon. Most stars spin to some degree. Our own Sun rotates at an equatorial speed of roughly 2 kilometers per second, completing one full rotation every 27 Earth days. That's leisurely by stellar standards. Even the fastest known neutron stars, so-called millisecond pulsars, can rotate hundreds of times per second, but these are the collapsed remnants of stars, tiny and dense, spinning like cosmic flywheels after catastrophic explosions. They're not massive main-sequence stars like VFTS 102. VFTS 102, on the other hand, is still in the prime of its stellar life. It's burning hydrogen in its core, forming heavy elements, shining brightly, and warping space around it with its mass and motion. And it's doing all of that while rotating at a speed that nearly rips it apart. This isn't a feature of its death. It's a fundamental part of how it lives. The idea that such a massive star could even survive this kind of spin is shocking. There's a hard limit in stellar physics known as the critical rotation speed. If a star spins any faster than this limit, the centrifugal force at its equator would exceed gravitational pull. The result? Mass loss, as the star would begin shedding its outer layers into space. Some fast rotators do this and are classified as B stars, which have gaseous disks of expelled material surrounding them. But even among B stars, few approach the limit as closely as VFTS 102. It is spinning so close to critical that a tiny increase in angular velocity could send it into rotational instability. And yet, it persists, holding itself together, barely, against the forces that threaten to tear it apart. Maintaining such a record is no small feat, especially considering the number of stars studied by astronomers in the past decades. Projects like the VLT Flames Tarantula Survey and countless spectroscopic surveys across the Milky Way and neighboring galaxies have measured the rotation rates of tens of thousands of stars. High-mass stars, low-mass stars, evolved stars, young protostars, and remnants. Yet in all these observations, none match the sheer velocity of VFTS 102. There have been contenders, of course. A few other O-type and B-type stars in the Milky Way and in the Magellanic Clouds have shown impressively high rotational speeds. One example is HD 191423, a fast-spinning O-star in our galaxy, which spins at approximately 450 km per second. Another is Zeta Ophiuchi, a well-known runaway star that clocks in around 400 km per second. And then there's a Kerner, a bright B star that rotates at nearly 90% of its critical speed, but even that only amounts to around 250 km per second. These are impressive speeds. But none come close to VFTS 102. At 600 km per second, it doesn't just outperform these stars, it doubles their output in rotational energy, and brings itself to the very precipice of what a star can physically endure. It's not just fast, it's nearly impossible. And so the question becomes, is VFTS 102 a cosmic fluke, or is it simply the first of a new class of extreme rotators that we've yet to discover? There's a growing recognition among astronomers that stars like VFTS 102 may be rare but not unique. The universe is vast, and rotational speeds depend on a range of factors: mass at birth, initial angular momentum, binary interactions, magnetic braking, and stellar winds. It's possible that other massive stars, in far-flung galaxies or shrouded in thick gas clouds, are spinning even faster but haven't yet been detected. But for now, VFTS 102 remains unmatched. Its record is also scientifically invaluable. By studying the limits of stellar rotation in such an extreme case, astrophysicists can refine models of how stars form, evolve, and die. The rotational data from VFTS 102 has already been fed into simulations and theories about gamma-ray bursts, core collapse dynamics, and black hole formation. It provides a kind of upper boundary condition, a benchmark against which other stars can be compared and contrasted. It helps answer the question, what happens when a massive star rotates as fast as it possibly can? There's also something poetically profound about this record. In a universe that stretches across billions of light years, filled with more stars than grains of sand on Earth, this one singular object stands as the fastest spinner of all massive stars. It is the Usain Bolt of stellar giants, the champion of angular velocity, spinning with such fury that even the laws of physics seem to hold their breath. How long it can keep that title is unknown. Perhaps future telescopes, like the James Webb Space Telescope or the upcoming Extremely Large Telescope, will uncover something even faster. Maybe in the depths of another galaxy, hiding behind dust or drowned in the light of a cluster, there's a star that spins even closer to self-destruction. But until that day comes, VFTS 102's record stands unchallenged, a monument to cosmic speed, resilience, and mystery. And so, in holding that record, it becomes more than just an object of interest. It becomes a symbol of the extremes the universe can reach, of the boundaries that are constantly being tested, and of the stunning variety found in the lives of stars. For now, and for the foreseeable future, VFTS 102 remains the fastest known massive star, and every photon it sheds is a reminder of what it means to spin at the limit of existence. In the vast catalog of stellar objects that astronomers have classified, measured, and modeled, VFTS 102 stands out not just for how fast it spins, but for how thoroughly it defies expectation. In a universe where the birth, life, and death of stars are generally governed by well-established physical laws and computer simulations, VFTS 102 is a glitch in the matrix, a cosmic anomaly whose very existence seems to violate the rules of stellar evolution. For this reason, it has earned the startling description among scientists as a star that shouldn't exist. Why does it defy our understanding? The issue lies in the fact that none of our standard models of star formation predict an object like this to naturally occur. The models say that stars form in rotating clouds of gas and dust, collapsing under gravity. Some angular momentum is retained, but as the cloud shrinks, excess angular momentum must be shed, otherwise the protostar would spin apart before it even forms. This is usually achieved through magnetic braking and mass ejection via protostellar jets. So even the fastest spinning newborn stars still emerge with rotation speeds far below their critical limit. And yet VFTS 102 is spinning at 600 km per second, a velocity that is dangerously close to the maximum threshold for stability. It did not just slip through the cracks of stellar physics, it tore through them. That raises a crucial question: how did it get this way? If VFTS 102 formed like a typical massive star, it should not have retained anywhere near this much angular momentum. During the early stages of star formation, massive stars are expected to lose much of their spin through radiation-driven winds, magnetic interactions with surrounding gas, and turbulent collisions. Furthermore, massive stars tend to form in crowded environments where nearby stars interact gravitationally, stealing or redistributing angular momentum. And if VFTS 102 had always been alone, these processes should have gradually slowed it down. But it didn't slow down, it accelerated. Which leads many astronomers to conclude that VFTS 102 didn't follow the typical path. Its current properties suggest that it may have formed through an unusual or rare process, possibly involving extreme binary interactions. As previously discussed, evidence points toward a violent past in a close binary system, where it likely accreted mass and angular momentum from a companion star, or even merged with it outright. This would explain not just its record-breaking spin but also some of its chemical features and motion through space. But even this explanation leads to further puzzles. If it was spun up by mass transfer, why didn't it lose spin again through magnetic braking? Why didn't strong magnetic fields emerge from the violent binary interaction, acting to slow it down? And if it's the product of a stellar merger, why isn't it showing signs of magnetic turbulence or instabilities that such events should leave behind? In short, no matter which scenario we plug into our models, something about VFTS 102 refuses to fit. Its spin is too high, its magnetic field too weak, its shape too distorted, and its motion through space too fast. It is the sort of object that forces scientists to return to the drawing board, not just to tweak parameters, but to ask whether we're missing entire processes in the way we think stars behave. This is why VFTS 102 is so invaluable. It is not just an oddity to marvel at, it is a challenge to our understanding. Science advances when theories meet anomalies, and this star is a glaring one. It suggests that there are pathways of stellar evolution we haven't fully explored, perhaps involving chaotic dynamics in crowded star-forming regions, or extreme episodes of mass transfer that leave behind rapidly spinning cores. Perhaps there are more VFTS 102-like stars out there, hidden in dusty nebulae, overlooked because they are transient, unstable, or obscured. Even the fact that VFTS 102 is still holding together is strange. Most stars that rotate this fast are expected to develop strong equatorial mass loss, forming disks or outflows. And yet VFTS 102 does not show the kind of thick, observable gas disk one would expect from a B star. It seems to balance at the edge of disintegration, but somehow, it does not tip over. Why? Is there some unseen factor, an internal mechanism or an external environment, that's helping it hold together? These are not trivial questions. If the answers lie in processes we haven't considered before, then VFTS 102 could be the first observable sign of a new class of stellar objects, extreme rotators born from rare cosmic events, short-lived but profoundly influential. They could help explain some of the strange explosions we've seen in other galaxies. They might be the precursors to gamma-ray bursts, or the progenitors of unusually massive black holes that we detect through gravitational waves. In that light, the phrase, "a star that shouldn't exist," becomes less a contradiction and more an invitation, a signpost that says we have more to learn. For astrophysicists, VFTS 102 is a living laboratory. It challenges the boundary conditions of rotation, mass loss, stellar shape, and magnetic field generation. It is a test of everything we believe we know about stars, and a beacon toward what we have yet to discover. And so, while it might baffle us, frustrate our simulations, and raise more questions than it answers, VFTS 102 plays a vital role in expanding our cosmic knowledge. In science, anomalies aren't failures, they're treasures. And this star, in all its violent, spinning glory, is among the most treasured of all. VFTS 102 already lives life on the edge, spinning so rapidly that its outer layers are constantly being pulled outward, straining against the inward pull of gravity. But what if it spun just a little bit faster? What if that delicate equilibrium, already near the breaking point, were nudged ever so slightly toward instability? The consequences would be catastrophic. In the balance between centrifugal force and gravity, there's a razor-thin line where the star can hold itself together. This limit is called the critical rotation velocity, the maximum speed at which a star can spin before the outward force at its equator exceeds the inward pull of gravity. For VFTS 102, which already spins at an estimated 600 km per second, it is terrifyingly close to that limit. Most estimates suggest that it's spinning at 95% to 99% of its critical velocity. If it were to exceed that limit, even by just a few percentage points, the centrifugal force at its equator would begin to win. Gravity would no longer be able to hold onto the star's outer layers, and they would begin to fly off into space, one wisp at a time at first, then in sweeping arcs of plasma and gas. The star would begin shedding mass at its equator in an uncontrolled, continuous release, forming a circumstellar disk of hot, glowing material. The spinning would essentially tear it apart from the outside in. This scenario isn't just theoretical. We see it happening to other stars, but none nearly as extreme as VFTS 102. Stars that hover close to their critical rotation speeds often display this kind of mass loss. These are the so-called B stars, massive stars surrounded by equatorial gas disks that have been flung off due to near-critical rotation. Their disks are visible in emission spectra and sometimes even with high-resolution imaging. But while B stars typically spin at 70% to 85% of their critical speed, VFTS 102 is pushing far beyond that. If it crosses the final threshold, it won't just become a B star, it could become an entirely new category of extreme rotator. Let's say for a moment that VFTS 102 were to be accelerated just slightly, perhaps by a residual gravitational interaction, or internal redistribution of angular momentum, or even by mass loss that paradoxically causes a spin-up effect due to conservation of angular momentum. That small increase could create runaway shedding, where material escapes in ever larger volumes. The resulting equatorial disk could become so dense that it obscures the star's surface, changes its spectrum, and affects its visibility from Earth. In extreme cases, such disks can cause the star's apparent brightness to vary over time as light is absorbed or scattered differently depending on the viewing angle. And the loss of mass isn't just cosmetic, it's profoundly disruptive. The internal structure of the star would change. With less mass, gravity weakens, and the fusion reactions inside the core could become unstable. Temperature gradients might shift. The pressure balance would collapse layer by layer. The shedding of the outer envelope could also strip the star of elements critical to its later fusion stages, meaning it could die prematurely or follow an entirely different evolutionary path. Moreover, once mass loss begins at this rate, it becomes increasingly difficult to stop. As the star loses mass, its shape becomes more distorted. The equator, now less gravitationally bound, becomes even more vulnerable to further shedding. It's a feedback loop. The more mass it loses, the faster it can spin, thanks to redistribution of angular momentum, and the faster it spins, the more mass it loses. Eventually, if this process continues unchecked, it could lead to the star tearing itself apart completely, not through a dramatic explosion like a supernova, but through a slow, spiraling unmaking. Over hundreds of thousands of years, a blink in stellar terms, VFTS 102 could be reduced to a bloated, irregular, partially naked core surrounded by a thick equatorial ring of expelled gases. A star dissolving into space, piece by glowing piece. There's also another possibility, that this spin-driven mass loss could trigger its death prematurely. If the outer layers are stripped too quickly, the star could be exposed to conditions that accelerate its core's evolution. The internal pressure would drop, fusion rates would spike, and the path to core collapse would be hastened. The result? A supernova that arrives earlier than expected. Or perhaps an even more exotic fate, a direct collapse into a black hole, without an intervening explosion, as the star crosses a mass threshold in its dying moments. In a universe that often moves at glacial paces, this scenario would be dramatic, even apocalyptic on cosmic scales. And it would all stem from a mere fractional increase in spin. A reminder of how delicately balanced massive stars like VFTS 102 truly are. Like a dancer on the edge of a cliff, one misstep would send it plummeting into oblivion. Interestingly, even if it never reaches that breaking point, the mere proximity to it makes VFTS 102 a laboratory for stellar physics. By studying its light, motion, and environment, astronomers can learn what happens in the final percentiles before critical velocity. It's a chance to study a star on the verge of rotational catastrophe, frozen in time at the threshold, giving us clues about how stars behave when pushed to their physical extremes. This is why the question, what if it spun faster, isn't just academic. It's a mirror held up to nature's tightrope walk, where rotation, gravity, pressure, and radiation perform a dance so precise that even the slightest imbalance could bring it all crashing down. And in VFTS 102, we find one of the most daring performers the universe has ever produced. As stars approach their critical rotation speed, the velocity at which centrifugal force at the equator nearly balances gravitational pull, they can begin to shed material from their equators into space. This material doesn't simply vanish. Instead, it accumulates, forming a thin, glowing disk that encircles the star like a luminous halo. These rotating giants, adorned with these gaseous rings, belong to a class of stars known as B stars. The B in B stands for the spectral type. These are hot, massive stars, typically classified as type B, meaning they are blue and extremely hot. The E refers to emission lines seen in their spectra, which are the key to identifying the presence of circumstellar disks. Normally, stars exhibit absorption lines in their spectra, where specific wavelengths are absorbed by elements in the stellar atmosphere. But in B stars, the surrounding disk of gas emits light at specific wavelengths, adding emission lines to the stellar spectrum. These lines are often most prominent in hydrogen, the Balmer series, revealing that the disk is made primarily of hydrogen gas ejected from the star itself. What causes the disk? It's the result of a complex interplay between rapid rotation, surface pulsations, and stellar winds. When a star spins at or near its critical speed, material at the equator becomes weakly bound. Any additional forces, such as magnetic fluctuations, convection bubbles, or pulsations from deeper within the star, can dislodge bits of plasma and fling them outward. Once freed, this material doesn't just escape into space. Instead, it settles into an orbiting disk, like water spinning off a wet tennis ball, except the water stays in orbit due to gravity and conservation of angular momentum. These disks are often temporary and dynamic. They can grow, shrink, dissipate, or reform over time. In some B stars, the disk persists for decades. In others, it appears and vanishes within years. The presence of a disk can affect the star's brightness, color, and spectral features, causing periodic dimming, brightening, or color changes as the disk grows more or less dense. Now, what about VFTS 102? Given its extreme rotation speed, one would logically expect it to be surrounded by a massive, bright equatorial disk, placing it squarely within the B star category. And indeed, some observations suggest it does exhibit features typical of B stars, particularly emission lines in its spectrum that hint at the presence of hot, orbiting gas. However, there's a curious twist. For a star spinning as fast as VFTS 102, the disk isn't as prominent or as luminous as one might expect. This presents a bit of a paradox. Is it that the disk is tenuous or difficult to detect due to its viewing angle or the local environment? Is the star losing material in a non-steady or eruptive way, unlike classical B stars? Or is something more exotic at play, where the star's mass, temperature, or lack of magnetic field alters how material is expelled and how long it persists in orbit? Some researchers have even speculated that VFTS 102 may represent an extreme subclass of B stars, or perhaps a precursor to a hyper-B star, a hypothetical category reserved for the most extreme rotators, balancing on the edge of mass loss instability, but not yet fully shedding material in a stable disk. It may be a missing link in the evolution of B phenomena, a snapshot of a star just before or after a major disk-forming episode. Moreover, the environment of VFTS 102 complicates matters. It resides in the Tarantula Nebula, a region bustling with ultraviolet radiation, shock waves from nearby supernovae, and strong stellar winds from other massive stars. This turbulent backdrop may affect how its own outflows behave, potentially disrupting or stripping away any disk that tries to form. It's possible that a fragile disk was present in the past, or that small-scale, intermittent shedding events occur but are swiftly erased by surrounding turbulence. Another factor is the inclination angle, the angle at which we're viewing the star. If we're looking nearly edge-on, the disk might be more visible, silhouetted against the star's light. But if we're looking pole-on, the disk may be nearly invisible to us, blending with the star's glare. In the case of VFTS 102, current evidence suggests we are seeing the star roughly equator-on, meaning any equatorial disk should be visible. So the absence of a strong, clear disk remains an open mystery. But despite these uncertainties, the underlying physics is solid. VFTS 102 is spinning fast enough to form a disk at any moment, if not already doing so in intermittent bursts. The high centrifugal forces are constantly weakening the gravitational grip at the equator, making it easier for surface material to escape. Even a slight change in the star's interior, such as a fluctuation in fusion rate or convective upwelling, could trigger a shedding event. In this way, VFTS 102 remains a B star in waiting, a celestial time bomb whose surface tension is one errant vibration away from collapse. If and when a large disk does form, it would provide an even more vivid example of how extreme rotation affects stellar evolution. The disk would become a source of spectral fingerprints, allowing astronomers to study its temperature, composition, rotation rate, and density. It would also influence the star's future, as continuous mass loss could significantly alter its lifespan, chemical balance, and the way it eventually dies. It's important to remember that B stars are among the most variable and enigmatic objects in the sky. Their disks are fleeting, mysterious, and tied intimately to the unstable boundary between gravitational control and rotational chaos. In VFTS 102, we may be seeing a star that doesn't just flirt with that boundary, it lives on it, day by day. And so, whether or not it currently wears a visible disk, the physics of B stars hangs heavily over VFTS 102's future. It may erupt into full B star behavior. It may flicker between disk-forming states. Or it may teach us something entirely new, offering insight into disk dynamics and ultra-fast rotators, especially those located in hostile environments like the Tarantula Nebula. One thing is certain, if VFTS 102 isn't yet a classic B star, it is hovering at the very threshold. The physics says it should be, and that means the star is either preparing to cross that line, or rewriting what we thought we knew about how and when such disks form. Even though VFTS 102 has already etched its name into the record books as the fastest spinning massive star ever observed, astronomers are far from done with it. In fact, they're just getting started. For the scientific community, VFTS 102 isn't just a star, it's a case study, a cosmic experiment that continues to unfold in real time. That's why researchers across the world are actively monitoring it, using some of the most advanced telescopes and instruments ever built, in an ongoing effort to understand its internal structure, external dynamics, and ultimate fate. Every time astronomers point a telescope toward the Tarantula Nebula, whether it's from the Atacama Desert or from orbit, they're watching VFTS 102. This star, spinning at the edge of physical limits, presents a tantalizing opportunity, the chance to observe a massive star as it flirts with instability, shedding light on phases of stellar evolution that are notoriously hard to witness. Scientists know that this star is not stable in the long term. Something will change. The question is when, and what signs will herald that change. One of the highest priorities for future observations is to monitor the star's spectral lines. Since VFTS 102 spins so rapidly, its spectral absorption lines are broadened dramatically due to the Doppler effect. By measuring these lines over time, astronomers can not only confirm its rotational speed but detect any variations in that speed. Even a small change could indicate an internal shift, perhaps the redistribution of angular momentum, or the beginnings of mass loss from the equator. High-resolution spectroscopy could also reveal the possible presence or absence of a circumstellar disk, particularly if the star transitions more clearly into B-star behavior. If an equatorial disk forms, astronomers will be able to study it in detail, using emission lines to determine its density, composition, and temperature. Any detection of a persistent hydrogen emission line would be a clear sign that the star is shedding material, and such an observation would not only validate predictions but also help track the rate and pattern of mass ejection. Meanwhile, infrared and ultraviolet imaging can provide additional information about VFTS 102's immediate environment. Since the Tarantula Nebula is a dense, chaotic region filled with dust, gas, and radiation from other massive stars, the external conditions around VFTS 102 are constantly in flux. Infrared observations allow scientists to penetrate that dust and directly image the surroundings of the star, searching for signs of expelled matter or interaction with nearby interstellar medium. Ultraviolet studies, on the other hand, can highlight high-energy processes on or near the star's surface, like shockwaves, stellar winds, or magnetic reconnection events, if they occur. Another promising avenue lies in polarimetry, the study of the polarization of light. If VFTS 102 begins to form a dense gas disk, or starts shedding mass more dramatically, the scattered light from these structures will often show distinctive polarization signatures. Continuous monitoring through polarimetric techniques can detect these subtle changes even before they become visible in standard imaging or spectroscopy. And let's not forget astrometry and proper motion tracking. One of the key clues to VFTS 102's origin was its unusually high speed through space, suggesting it was ejected from its original location, likely by a supernova blast from a former binary companion. Continued observations of its trajectory through the Large Magellanic Cloud may help pinpoint its past position more accurately, revealing exactly where it came from and how long ago the separation occurred. If researchers can map its motion backward in time with greater precision, they may even locate the remains of its former companion, perhaps a neutron star or pulsar. Additionally, as telescopes become more sensitive, we may soon be able to detect variations in the star's brightness, even small ones. These could indicate surface pulsations, star spot activity, or outbursts of material from the equator. Some massive stars show quasi-periodic brightening or dimming as their internal structure subtly changes. For a star rotating as fast as VFTS 102, any instability, no matter how minor, might present as a warning sign that something larger is about to occur. Upcoming and next-generation telescopes will be instrumental in this effort. The James Webb Space Telescope, JWST, with its infrared capabilities, could observe the dusty regions around VFTS 102 in unprecedented detail. The extremely large telescope, ELT, under construction in Chile, will provide unmatched resolution for studying stars and other galaxies. Instruments like the Square Kilometre Array, SKA, could even detect radio emissions from a neutron star companion, if one exists, or from turbulent plasma around VFTS 102's surface. In the meantime, data from legacy telescopes, like the Very Large Telescope, VLT, and the Hubble Space Telescope, continue to be reanalyzed. As computational methods improve, astronomers can extract even more insight from older data, uncovering subtle patterns that were previously missed. Machine learning algorithms are being developed to track changes in stellar spectra over time, flagging anomalies that human eyes might overlook. The long-term goal is to catch VFTS 102 in the act, to witness a transition, an outburst, or even the beginning of its final collapse. If the star undergoes a gamma-ray burst, scientists hope to identify it in real time, connecting the event to a well-studied progenitor. Or if the star begins to break apart via mass loss, astronomers want to track the early stages of that disintegration, frame by frame, to better understand how fast rotators die. There is also a more philosophical reason to keep watching. VFTS 102 is rare. Most massive stars don't rotate this fast. Many don't live long enough to display such exotic behavior. To have one of these stars in our observational reach, just 160,000 light-years away, in a well-studied nebula, visible from the southern hemisphere, is a stroke of incredible luck. It may be decades or even centuries before another star like this is found, let alone so well placed for monitoring. In the meantime, VFTS 102 is our window into extremes. It's not just about studying the star itself. By observing its behavior, we gain insight into a much broader set of astrophysical phenomena: stellar evolution, binary dynamics, rotational physics, mass loss, and end-of-life behavior in massive stars. Each new observation adds a data point, helping build a more complete picture of how the universe works at its most energetic and unstable. In many ways, VFTS 102 has become a kind of cosmic clock, ticking toward a moment that no one can predict. Will it explode? Collapse into a black hole? Spin itself into fragmentation? Or will it surprise us entirely, doing something no model has yet imagined? For now, the only answer is to keep watching and waiting. Despite everything we've uncovered about VFTS 102, the blistering speed, the immense mass, the unusual movement, and the spectral fingerprints that hint at a chaotic past, there's still an overwhelming sense of mystery surrounding this star. It's not just an extreme object, it's an unresolved puzzle, one that defies straightforward classification. Every answer we've gained from observing this stellar enigma has simply unveiled a new layer of questions, and some of the most critical of these remain uncomfortably unanswered. First, there's the question of how it formed. VFTS 102's origin remains murky. Traditional stellar formation models simply don't account for stars spinning this fast. As mentioned earlier, angular momentum must be shed during star birth to prevent a protostar from tearing itself apart. So how did VFTS 102 end up spinning at almost its critical limit? Was it born spinning like this from the beginning, perhaps in a part of the Tarantula Nebula with unusual angular momentum conditions, or did it acquire this incredible speed through a process after birth? The leading theory suggests it once belonged to a binary system, and that a companion star transferred mass and momentum onto VFTS 102, spinning it up in the process. But this scenario, while compelling, isn't confirmed. It relies heavily on indirect evidence, its high space velocity, signs of past mass transfer, and the possibility of a nearby neutron star or pulsar. But where is this companion now? If it went supernova, shouldn't there be a detectable remnant, a glowing neutron star or a high-energy pulsar with a known spin signature? And if there is one nearby, how do we prove it was once bound to VFTS 102 and not just another random inhabitant of the Tarantula Nebula? Even if the binary hypothesis holds, it leads to new unknowns. How close were the stars? How much mass did VFTS 102 steal? How long ago did the supernova occur? The details of this interaction matter, because they could explain not only the star's speed but its internal structure, surface composition, and future behavior. Right now, these questions are constrained by observational limits. The region around VFTS 102 is crowded, dynamic, and dusty, and the trail of evidence is faint, perhaps permanently smeared out by time and radiation. Then there's the deeper mystery of the spin itself. We know how fast it is, but we don't yet fully understand what that speed is doing to the star internally. Is angular momentum distributed evenly throughout the stellar interior, or is it concentrated in the outer layers? If it's unevenly distributed, could that lead to internal shear instabilities, regions where different layers of the star are rotating at different speeds, generating turbulence, mixing, or even bursts of magnetism? Our models can simulate these processes, but direct observational evidence is almost impossible to come by. We can't see inside the star, and we don't yet have the tools to map its internal spin gradient. Which leads to yet another problem, the magnetic mystery. Why is a star spinning this fast not exhibiting strong magnetic fields? In theory, fast rotators like this should generate powerful dynamos, producing magnetic fields that manifest as star spots, flares, or wind modulation. But VFTS 102 doesn't show any clear signs of such activity. Could it be that the internal conditions of the star suppress magnetism? Is there an exotic balance between spin and internal pressure that inhibits magnetic generation? Or are the magnetic fields there, just hidden in a way we can't detect yet? And then, of course, there's the final question that looms over every observation, every hypothesis, every simulation: how will it die? VFTS 102 is living on borrowed time. As a massive star, it is destined for a violent end. But the details of that ending are far from settled. Will it go supernova, ejecting outer layers in a brilliant explosion before leaving behind a neutron star or black hole? Will it skip the explosion entirely and collapse directly into a black hole, too massive to resist its own gravity? Or will it meet its fate in the most extreme way possible, by becoming a long-duration gamma-ray burst, one of the most energetic events the universe can produce? If it does die as a gamma-ray burst, when will it happen? And would we be able to detect it from Earth? The Large Magellanic Cloud is about 160,000 light-years away, close enough that a GRB from VFTS 102 aimed directly at us would be observable, but not close enough to pose any danger to our biosphere. Still, such an event would be monumental, not just for its spectacle but for its scientific implications. It would allow astronomers to link the GRB directly to a known progenitor, solving long-standing questions about the origins of these cataclysmic events. But again, we don't know if that's how it will end. Maybe it will flare out in a violent mass-shedding episode long before then. Maybe it will collapse quietly, its death hidden behind a thick veil of plasma and dust. Maybe something even stranger will happen, some new, poorly understood pathway of stellar death that we have yet to observe in real time. And that's not the end of the unknowns. VFTS 102 is teaching us that there may be entire categories of stars that we don't yet recognize. What if this star is just the tip of the iceberg? What if there are other ultra-fast rotators out there, hidden by dust, outshone by neighbors, or too far for our current instruments to resolve? Are there galaxies where these kinds of stars are common instead of rare? And if so, what does that mean for our understanding of how galaxies evolve, how heavy elements are forged, and how black holes form? Even its location presents questions. Why did such a rare star emerge in the Tarantula Nebula? Is that region special in some way, denser, more chaotic, or more conducive to producing extreme objects? Or is it simply that we're looking more closely at this region than others? Could similar stars be hiding in our own galaxy, waiting for us to find them? Each of these questions is like a thread, woven into the complex tapestry of VFTS 102's story. Pull on any one of them and it leads to other stars, other systems, other forces at play in the universe. And as we continue to observe, model, and theorize, VFTS 102 stands as a reminder of how much we still don't know, and how much more there is to discover. It's easy to forget that in the age of exoplanets, black holes, and gravitational wave astronomy, there are still basic stellar phenomena that confound us. But VFTS 102 brings us back to the fundamentals. A star. Spinning. Too fast. Too strange. Too bold to ignore. It humbles us. Challenges us. Invites us to look deeper, to push harder, to keep asking questions, even when we think we know the answers. VFTS 102 isn't just a fascinating star, it's a living laboratory, a one-of-a-kind natural experiment where the rules of stellar physics are stress-tested to their absolute limits. In a universe governed by the subtle balance of forces, VFTS 102 boldly inhabits the outermost edge of stability. Every rotation, every wisp of plasma that clings to its equator, every pulse of energy surging from its core, is an ongoing demonstration of extremes in action. And that makes it more than just a record breaker. It makes it a classroom for the cosmos. In many ways, stars like VFTS 102 are proving grounds for our most complex models. Traditional astrophysics, born from centuries of observation and refined by decades of simulation, gives us reliable rules for most stars. We understand how average stars like our Sun live and die. We can predict how red giants expand, how white dwarfs cool, and how supernovae explode. But VFTS 102 breaks the mold. It spins too fast, evolved too strangely, and lives too violently for our neat, tidy equations to apply without hesitation. This is why it's so important, not just as an oddity, but as a benchmark. Scientists can plug its values into their computational models, mass, rotation, temperature, luminosity, chemical composition, and see what those models predict. Do they break down? Do they produce results that match observation? Or do they yield new insights into nonlinear dynamics, angular momentum conservation, and relativistic plasma behavior? One key area where VFTS 102 acts as a testbed is in the physics of rotation. Spin is a fundamental parameter in astrophysics, but stars spinning this fast are rare, and observational data is sparse. With VFTS 102, researchers can study how extreme angular momentum affects stellar structure. Does the core rotate at the same speed as the envelope? How is energy transported through a rapidly rotating star? Are traditional models of convection and radiation still valid? Or are there emergent behaviors, new forms of internal turbulence, for example, that only show up under these conditions? And then there's the effect of spin on gravity and shape. VFTS 102 isn't a sphere, it's an oblate spheroid, stretched at the equator and compressed at the poles. This distortion isn't just cosmetic. It changes how energy escapes the star, how mass loss occurs, and how gravity itself behaves across the surface. By observing and modeling the differences in temperature and brightness between the equator and the poles, what we call gravity darkening, scientists can test gravitational and radiative theories that are otherwise impossible to examine with slow rotators. Another layer of this natural experiment comes from the chemical composition of VFTS 102. Massive stars like it undergo rapid fusion, forging heavier elements in their cores and often dredging some of that material to the surface through convection and rotational mixing. Because VFTS 102 spins so quickly, the mixing is likely far more intense and chaotic than in standard models. Observing its spectral lines helps scientists see what elements are present on the surface, and in what ratios, giving clues about what's happening inside. Are the surface layers enriched with nitrogen or helium? Are they depleted of lighter elements? And how do those patterns compare to slower spinning siblings? Equally fascinating is the star's behavior in the context of stellar evolution. At 25 times the mass of the Sun, VFTS 102 is destined for a dramatic end. But its rotation complicates everything. Models show that stars with high spin rates lose mass differently, evolve more quickly, and may follow alternate evolutionary tracks entirely, possibly bypassing supernovae or evolving into exotic objects like collapsars, which can give rise to long-duration gamma-ray bursts. Studying this star over time, tracking its luminosity, temperature, wind speeds, and spectral shifts gives scientists the rare chance to calibrate those evolutionary models. VFTS 102 also provides a controlled setting for testing ideas about binary interactions. If it did gain its speed through mass transfer from a former companion, then its composition, trajectory, and internal structure all carry fingerprints of that process. Comparing it to other post-interaction systems helps researchers refine their theories about binary star life cycles, how close pairs form, how mass is transferred, and how stars can be dramatically reshaped by their neighbors. But the experimental value doesn't stop at the star itself. VFTS 102 exists within a specific environment, the 30 radius region of the Tarantula Nebula, which is one of the most active stellar nurseries in the nearby universe. The nebula is filled with radiation, stellar winds, and the remnants of countless past supernovae. It's a pressure cooker of star formation, chaos, and high-energy phenomena. By situating VFTS 102 within this environment, scientists can explore how external conditions affect extreme stars. Does the surrounding radiation field enhance or suppress its mass loss? Are shockwaves from nearby explosions influencing its rotation or evolution? Is it accreting material from its environment, or carving out a cavity with its stellar wind? It's not an exaggeration to say that nearly every field of stellar physics, thermodynamics, hydrodynamics, radiation transport, nuclear fusion, plasma physics, magnetism, and relativistic motion, can be exercised, validated, or challenged by studying VFTS 102. It is a crucible in which the universe has mixed the most volatile ingredients, turned up the pressure, and let the laws of nature play out with the volume turned all the way up. And this is why scientists aren't just watching VFTS 102. They're learning from it, publishing papers, revising models, and developing new tools specifically because of what this one star is telling them. It's teaching us about the boundaries of survivable spin. It's revealing how stars can thrive, or barely survive, when the rules are pushed to their breaking point. It's reminding us that the universe is far more diverse, more dynamic, and more surprising than even our most powerful theories can predict. In a cosmos full of stars that follow the rules, VFTS 102 is the rare exception, a rebel, a test case, a glitch in the matrix that dares us to explain it. And for as long as it lives, it will continue teaching us things no textbook ever could. In the end, VFTS 102 stands not merely as a star, but as a symbol of cosmic rebellion, a defiance of the limits we once believed stars couldn't cross. In a universe filled with the quiet rhythm of stars born, burning, and fading away in slow, predictable arcs, this one chose to race instead. To burn faster, spin harder, and dare gravity to keep it whole. It is the outlier, the exception, the rule-breaker blazing across the canvas of the Tarantula Nebula with a velocity so extreme that it nearly tears itself apart. Its story is one of survival against the odds. It may have been forged in companionship, a once-balanced binary system that was violently broken when one star exploded, throwing VFTS 102 into the void, faster, heavier, and far more unstable than it had ever been. That explosion, that moment of death, may have been VFTS 102's own moment of rebirth, transformed not into wreckage, but into a juggernaut, a stellar cyclone spinning faster than any other massive star we've ever seen. But for all its power and speed, VFTS 102 is not invincible. It's running a race it cannot win, not against time, not against the laws of physics. Its own momentum will be its undoing. With every rotation, it balances closer to the brink. One pulse too strong, one tremor too deep, and the star may tip into a state from which it cannot return. Whether it spins itself into disintegration, sheds its layers to space in a storm of gas and plasma, or finally collapses in a blaze of gamma radiation and forms a black hole, Its fate is sealed by the very force that makes it exceptional. Yet before that moment comes, before the final breath, the last photon, the great silence, VFTS 102 offers us a rare and precious gift, a glimpse into what the universe can create when it stops playing safe. It reveals how stars can live not just long, but intensely. How the violent, spinning chaos of stellar interiors becomes the sculptor of destiny. How from the wreckage of a companion and the furnace of the nebula, something astonishing can emerge, a celestial engine roaring at hundreds of kilometers per second, threatening to fling its own skin into space with every turn. It forces us to revise our models, rethink our definitions, reimagine what a star can be. For those who study the skies, VFTS 102 is like a whisper from the edge of possibility, a reminder that nature doesn't abide by the neat categories we create for it. There are no rules, only tendencies. There are no certainties, only probabilities. And sometimes, just sometimes, the improbable happens. So, we continue to watch. Not just because of what might happen, but because in its very existence, VFTS 102 asks questions no one else can. It tells us what it means to live on the edge of destruction. It lets us peer into the margins of astrophysics, into those hazy boundaries between order and chaos. And even in silence it speaks. It speaks of ancient violence and future catastrophe. It speaks of gravity pushed to its limits and light stretched by speed. It speaks of the dance between mass and motion, the unwritten rules of stellar death, and the awe-inspiring scale of cosmic time. VFTS 102 is not a gentle star. It does not twinkle. It rages. It spins. It races. And one day, when that race is over, when the last photon flees from its shredded core, when the final collapse compresses its mass into the unseen, we will remember it not as a mystery solved, but as a question beautifully asked. Because in a universe that plays by its own rules, sometimes a single star can remind us why we look up at all. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.